Mercury, the smallest planet in our solar system. A scorched, cratered wasteland barely larger than our moon, spinning slowly in the fierce glare of the sun. For decades, textbooks described it as geologically dead, nothing more than a relic frozen in time since the solar system's violent birth 4.5 billion years ago. Scientists looked at this tiny world, baking relentlessly under solar radiation 7 times more intense than what Earth receives, and they assumed its story had ended eons ago. Whatever internal heat had once driven volcanic eruptions and tectonic activity, they reasoned, must have radiated away into space billions of years in the past. The planet should be cold, rigid, utterly lifeless in the geological sense. A cosmic fossil, interesting only for what it could tell us about the ancient past, not about processes happening today. But here's the thing. They were completely wrong. Mercury isn't dead, not even close. It's shrinking. Right now, as you listen to this, Mercury's surface is cracking, buckling, and folding in on itself like a deflating balloon. Giant cliffs hundreds of kilometers long are forming, rising kilometers above the surrounding plains, as the planet's interior cools and the whole world contracts. Fault systems that first formed billions of years ago are slipping again today, generating quakes that rumble through the planet's interior. And that's just the beginning of Mercury's secrets. This tiny world, orbiting closer to the Sun than any other planet in our neighborhood, closer even than blazing Venus, harbors mysteries that challenge everything we thought we knew about how planets work, how they form, and how they evolve over cosmic time. A liquid core that shouldn't exist, that defies every prediction our models make about how quickly small planets should cool. Ice, actual water ice, hiding in perpetual darkness at the poles, existing in the single most unlikely place you could imagine finding frozen water in the entire solar system. Strange, bright depressions called hollows, appearing across its surface, actively eating away at the rock itself through processes we're still struggling to understand. Fresh fault scarps forming today, some of them so young they could have appeared within the last few million years, maybe even more recently. And a magnetic field, weak but persistent, that tells us the planet's heart is still molten, still churning, still generating electromagnetic forces after 4.5 billion years. If you're ready to explore the solar system's most underrated mystery, to discover why Mercury breaks virtually every rule we've ever established for how planets should behave, hit that like button and subscribe, because we're about to dive deep into the weird, wonderful reality of this misunderstood world. So what exactly is happening on this tiny world? What forces are at work beneath that cratered surface? And why does Mercury break so many of the rules we've established for how planets should behave? To understand the significance of what we're seeing on Mercury, we need to appreciate just how strange this planet really is. Mercury sits just 58 million kilometers from the Sun on average, though its highly elliptical orbit brings it as close as 47 million kilometers and swings it out to 70 million. From its surface, our star looms 3 times larger than it appears from Earth and shines 11 times brighter. The sunlight is so intense that surface temperatures on the day side can reach 430 degrees Celsius, hot enough to melt lead, hot enough to make tin flow like water. And yet, despite this proximity to the Sun, despite being the closest planet to our star, Mercury is not the hottest planet in our solar system. That distinction belongs to Venus, whose thick atmosphere traps heat like a planetary greenhouse, creating surface temperatures that exceed Mercury's, even though Venus orbits twice as far from the Sun. Mercury, by contrast, has virtually no atmosphere to speak of, just a thin exosphere, a barely there scattering of atoms blasted from its surface by the solar wind and micrometeorite impacts. This isn't an atmosphere in any meaningful sense. It's so tenuous that the atoms in Mercury's exosphere rarely collide with each other. They follow ballistic trajectories, arcing up from the surface and falling back down like tiny spacecraft, or escaping into space entirely. Without an atmosphere to distribute heat, Mercury experiences the most extreme temperature range of any planet in our solar system. When the Sun sets on Mercury, temperatures plummet to minus 180 degrees Celsius. That's a temperature swing of more than 600 degrees between day and night, from hot enough to melt metal to cold enough to freeze carbon dioxide solid. Mercury's day is also extraordinarily long. The planet rotates on its axis once every 59 Earth days, while completing an orbit around the Sun every 88 Earth days. This creates a peculiar 3-to-2 resonance, discovered by the Italian scientist Giuseppe Colombo in the 1960s. For every 2 orbits Mercury makes around the Sun, it rotates exactly 3 times on its axis. This means that from sunrise to sunset on Mercury takes 176 Earth days, nearly 6 months of continuous scorching sunlight, followed by 6 months of frigid darkness. If you could stand on Mercury's surface, you'd watch the Sun creep across the sky with agonizing slowness, taking 88 Earth days to traverse from horizon to horizon. And Mercury's orbital path is far from circular. Its distance from the Sun varies dramatically, making its orbit the most eccentric of any planet in our solar system. This elliptical orbit, combined with that strange rotational resonance, creates what astronomers call hot poles. Certain longitudes on Mercury's equator receive significantly more solar radiation than others because of where the planet is in its orbit when that longitude faces the Sun. These permanent hotspots on the surface experience even more extreme temperatures than the already scorching average. At the hot poles, surface temperatures can reach 450 degrees Celsius during the long Mercurian day. With a diameter of just 4,880 kilometers, Mercury is only slightly larger than our Moon. Earth's Moon measures 3,475 kilometers across, making Mercury only about 40% larger. You could fit more than 18 Mercuries inside Earth. The entire planet would fit comfortably within the continental United States with room to spare. And yet, despite its diminutive size, Mercury is the second densest planet in the solar system, exceeded only by Earth itself. Mercury's density is 5.4 grams per cubic centimeter. Earth's density is 5.5. But here's the thing. Earth's high density comes partly from gravitational compression. The immense weight of Earth's outer layers squeezes the core, making the whole planet denser. Mercury doesn't have nearly as much mass, so it doesn't experience the same compression. If we account for the compression effect and compare what's called uncompressed density, Mercury is actually denser than Earth. For a planet so small, this density is profoundly strange. Planetary scientists have calculated that Mercury's enormous iron core must make up about 85% of the planet's radius. To put that in perspective, that means if you could cut Mercury in half and look at a cross-section, the iron core would dominate the view, with only a thin shell of rocky material surrounding it. That's a metal-to-rock ratio unlike anything else in the inner solar system. Earth's core makes up only about 55% of its radius. Mars has a core that's roughly 40% of its radius. Venus, which is nearly Earth's twin in size, has a core making up about 30% of its radius. Our Moon's core is tiny, only about 20% of its radius. Mercury stands out as bizarre, a planet that's almost all core with just a thin rocky veneer. Something about Mercury's formation process left it with far more metal than it should have. For decades, scientists have proposed different theories to explain this anomaly. Maybe a giant impact stripped away most of Mercury's rocky mantle early in its history, leaving behind a proportionally larger core. Picture a collision with another planetary body during the chaotic early days of the solar system, violent enough to blast away the outer rocky layers, but not energetic enough to destroy the planet entirely. The iron core would survive, but much of the lighter rock would be ejected into space or vaporized. Perhaps Mercury formed from materials that were inherently metal-rich, closer to the Sun, where rocky materials couldn't easily condense from the solar nebula. In the intense heat near the young Sun, silicate minerals might have remained vaporized while iron and other metals could still condense into solid grains. These metal-rich grains would then accumulate to form Mercury, creating a planet with an unusually large core from the start. Or maybe intense solar radiation vaporized and blew away lighter elements during the planet's formation, concentrating the heavier metals. The young Sun was more active and energetic than it is today, producing powerful stellar winds that could have swept through the inner solar system like a cosmic broom, carrying away lighter materials but leaving the heavy iron behind. Each theory has its merits, and each has its problems. The giant impact theory struggles to explain why we don't see more debris from such a catastrophic collision in Mercury's vicinity. The metal-rich formation zone theory has trouble accounting for the presence of volatile elements like sulfur that we've now discovered on Mercury's surface. The solar wind stripping theory faces questions about whether even the young Sun's winds were powerful enough to selectively remove so much rocky material while leaving the metal behind. Scientists continue to debate these scenarios, refining models and searching for evidence that might favor one explanation over the others. But whatever the cause, Mercury's oversized core sets the stage for the first of our planet's great mysteries, because that enormous core, according to everything we know about planetary physics, according to every thermal evolution model we've built, shouldn't still be liquid. Small planets cool quickly. This is a fundamental principle of planetary science, as certain as gravity itself. Mercury has less than half the diameter of Earth, which means it has much less volume relative to its surface area. Heat escapes through a planet's surface. The larger the surface area compared to the volume, the faster heat can escape. Think of how a cup of coffee cools faster than a large pot. The cup has more surface area relative to its volume, so heat escapes more efficiently. The same principle applies to planets, just on a vastly larger scale. With Mercury's small size, its core should have solidified billions of years ago, becoming a cold, dead lump of iron at the planet's heart. The heat generated during Mercury's formation, the radioactive decay of elements in its interior, the energy released as the core crystallizes and differentiates, all of this should have radiated away into space long ago. By all rights, Mercury should be geologically dead, with a solid core, no internal convection, and no ongoing geological activity whatsoever. And yet, in 1974, NASA's Mariner 10 spacecraft made 3 flybys of Mercury and detected something unexpected. A magnetic field, a global magnetic field, weak but unmistakable, extending around the entire planet like an invisible shield. This discovery shocked the scientific community and sparked decades of debate about what it could possibly mean. Magnetic fields around planets are generated by what's called a dynamo effect. Deep inside a planet, electrically conductive material, typically molten iron, flows in convective patterns. These flowing currents of liquid metal generate electrical currents through a process called electromagnetic induction. The electrical currents, in turn, produce magnetic fields. It's the same principle that makes an electric generator work, just operating on a planetary scale. But this dynamo mechanism requires very specific conditions to function. The conducting material must be liquid, not solid. A solid core can't flow, can't convect, can't generate the currents needed to produce a magnetic field. There must be convective motion within that liquid. The fluid needs to be rising in some places and sinking in others, driven by temperature differences or compositional variations. Without this motion, even a liquid core won't generate a field, and the planet must be rotating, providing the Coriolis effect that helps organize those currents into a coherent, stable field. The Coriolis effect, the same force that shapes weather patterns on Earth, causes the convecting fluid to swirl and twist in organized ways, amplifying and sustaining the magnetic field. Mars provides a cautionary tale. Once, billions of years ago, Mars had a magnetic field. We can see the evidence frozen into ancient rocks on its surface, magnetized billions of years ago when the Martian dynamo was active. Instruments on orbiting spacecraft have detected these magnetic anomalies, particularly strong in the ancient southern highlands. They tell us that early Mars had a churning, convecting core, generating a global magnetic field, strong enough to protect the planet from the solar wind. But Mars is small, even smaller than Earth, though substantially larger than Mercury. Its core cooled relatively quickly on geological timescales, and the dynamo shut down about 4 billion years ago. Magnetism. Today, Mars has no global magnetic field, just remnant magnetization in its ancient crust, fossil evidence of a magnetic field that died when the planet's heart grew cold. Venus, nearly Earth's twin in size, also lacks a global magnetic field, though for different reasons. Venus is large enough that its core should still be at least partially molten, but Venus rotates incredibly slowly, taking 243 Earth days to complete a single rotation. This slow rotation may not provide enough Coriolis effect to organize the core's convective currents into a coherent dynamo. Or Venus may have a different internal structure that prevents the kind of convection needed to generate a field. The exact reason remains unclear, but the result is the same. No dynamo, no magnetic field. Given these examples, Mercury's magnetic field seemed impossible. Planet 1/3 the size of Earth, with less than 6% of Earth's mass, with a surface area less than that of the Atlantic Ocean, should not be able to maintain a liquid core for 4.5 billion years. The heat should have escaped long ago. The core should be solid. The dynamo should be dead. When Mariner 10 first detected Mercury's field during its flybys in the mid-1970s, some scientists suggested it might be remnant magnetism, similar to Mars. Perhaps Mercury's rocks had been magnetized billions of years ago when the planet did have an active dynamo, and we were merely seeing fossil magnetism, ancient fields locked into the crust. But the field detected by Mariner 10 was too strong and too organized to be remnant magnetism. Crustal magnetization creates localized anomalies, patchy regions of stronger and weaker field scattered across the surface. Mercury's field was different. It was global, coherent, and clearly generated by some active process deep within the planet. The only explanation was that Mercury's core, or at least part of it, remained liquid. But how? How could such a small planet retain enough internal heat to keep its core molten after billions of years? This became one of the great puzzles of planetary science, a mystery that would take decades and a dedicated orbiter mission to begin unraveling. 3 decades passed. During those years, scientists developed increasingly sophisticated models of planetary thermal evolution, refined our understanding of how planets cool and how dynamos operate, and waited for the technology to advance enough to send another mission to Mercury. Ground-based observations continued to track Mercury as it crossed the Sun's disk during transits, studied its surface through telescopes, and monitored its thin exosphere. But these observations couldn't answer the fundamental question about the core. Only a spacecraft in orbit around Mercury, making detailed measurements over an extended period, could do that. Finally, in 2004, NASA launched MESSENGER, the Mercury surface, space environment, geochemistry, and ranging spacecraft. DALI, after a complex series of gravity assist maneuvers past Earth, Venus, and Mercury itself, carefully choreographed to slow the spacecraft down and match velocities with the innermost planet, MESSENGER finally entered orbit around Mercury in March 2011. It was a triumph of orbital mechanics, the first spacecraft to ever orbit Mercury, arriving after a journey of more than 6.5 years, covering billions of kilometers. For the next 4 years, MESSENGER mapped every square meter of Mercury's surface, analyzed its composition with a suite of scientific instruments, measured its magnetic field with unprecedented precision, and monitored how the planet wobbled on its axis. That wobble, called libration, proved crucial to understanding Mercury's interior structure. As Mercury orbits the Sun, tidal forces cause the planet to rock back and forth very slightly, like a child's toy that wobbles but doesn't fall. This happens because Mercury's orbit is elliptical rather than circular. When Mercury is closer to the Sun at perihelion, the Sun's gravitational pull is stronger. When it's farther away at aphelion, the pull is weaker. These changing tidal forces, combined with Mercury's peculiar 3:2 spin-orbit resonance, cause the planet to librate, to wobble in its rotation. The amplitude of this wobble depends on what's inside the planet. If Mercury had a completely solid interior, it would wobble in one way. If it had a liquid outer core surrounding a solid inner core, it would wobble differently. The liquid layer acts like a cushion, allowing the outer rocky shell to move more freely relative to the deep interior. By measuring the amplitude of Mercury's libration with extraordinary precision, tracking how much the planet wobbles back and forth over the course of its orbit, scientists could determine whether Mercury's core was solid or liquid. MESSENGER carried a laser altimeter that bounced laser pulses off Mercury's surface, measuring the distance with incredible accuracy. Over years of observations, watching the same surface features appear and reappear as Mercury rotated, the spacecraft could detect subtle changes in where those features appeared. These shifts, tiny variations measured in meters across a planet, thousands of kilometers wide, revealed the amplitude of Mercury's libration. The measurements were unambiguous. Mercury wobbles too much to have a solid core. The data clearly indicated that Mercury's core contains a liquid outer region surrounding a solid inner core, much like Earth's structure. The liquid outer core extends from about 2,000 kilometers depth to roughly 400 kilometers below the surface. That's a massive ocean of molten iron and nickel, perhaps 1,500 kilometers thick, churning in the darkness beneath Mercury's sun-baked crust. This wasn't just a minor discovery. It fundamentally changed how we understand Mercury. The planet isn't a dead ball of rock and iron. It has an active interior with liquid metal flowing and convecting deep below the surface. That liquid core is what generates the magnetic field Mariner 10 detected. The mystery wasn't solved, though. In fact, it deepened. Now we knew for certain that Mercury had a liquid core, which made the question even more pressing. How can such a small planet maintain a liquid core after 4.5 billion years? But this confirmation only deepened the mystery. How can such a small planet maintain a liquid core? What's keeping that iron molten after billions of years? The answer, scientists believe, lies in Mercury's composition. The core likely contains significant amounts of lighter elements mixed with the iron. Sulfur is the primary candidate. Sulfur has a much lower melting point than pure iron. Pure iron melts at about 1500 degrees Celsius. But if you mix sulfur into the iron, forming what's called an iron-sulfur alloy, the melting point drops significantly by hundreds of degrees. This is the same principle behind salt lowering the freezing point of water on icy roads. Mixed into the core, sulfur acts like antifreeze for iron, lowering the temperature required to keep the metal molten. Messenger's measurements of Mercury's surface composition revealed surprisingly high concentrations of sulfur supporting this theory. The spacecraft's X-ray spectrometer detected sulfur abundances much higher than anyone expected. If the surface rocks contain so much sulfur, it's reasonable to think the core does too. During Mercury's formation, sulfur from the solar nebula would have been incorporated into the iron as the planet grew. That sulfur-rich iron sank to form the core, and it's been there ever since, keeping the core's melting point low enough for at least the outer part to remain liquid. But sulfur presents its own puzzle. According to our models of solar system formation, volatile elements like sulfur shouldn't exist this close to the sun. The young sun's intense heat should have driven these lighter materials outward early in the solar system's history, leaving the inner regions depleted of volatiles. Earth has relatively little sulfur compared to the outer planets and their moons. Mercury, being even closer to the sun, should have even less. And yet, Messenger found that Mercury's surface rocks contain sulfur concentrations comparable to Mars, a much colder world that formed farther from the sun. How did Mercury accumulate so much of this volatile element? How did it avoid losing its sulfur when the young sun should have been blasting it away? Recent research suggests the answer might involve what scientists call iron snow. Yes, you read that correctly. Iron snow falling through Mercury's core. The concept sounds bizarre, but the physics makes sense. Here's how it works. At the boundary between the liquid outer core and the solid inner core, deep inside Mercury at pressures millions of times higher than atmospheric pressure and temperatures around 2000 degrees Celsius, the temperature and pressure are just right for iron to crystallize out of the liquid metal mixture. These tiny crystals of pure iron form in the liquid, microscopic metal snowflakes drifting through an ocean of molten metal. These iron crystals are denser than the surrounding liquid, which makes sense because solid iron is denser than liquid iron. So they sink inward under Mercury's gravity, like snow falling through air. Except this snow is made of iron, and it's falling through liquid metal under incredible pressure. As these iron crystals drift downward and accumulate, they add to the solid inner core, causing it to grow slowly over time. But as the iron crystallizes, It leaves behind the sulfur and other lighter elements in the liquid. Pure iron crystallizes, but the sulfur stays dissolved in the remaining molten metal. This sulfur-enriched liquid becomes buoyant compared to the iron-poor liquid below it. Think of oil floating on water. The sulfur-enriched liquid is less dense, so it rises toward the top of the outer core. This upward and downward motion, iron snow sinking while sulfur-rich liquid rises, creates convection currents throughout the liquid outer core. These currents aren't gentle. They're vigorous flows, churning through hundreds of kilometers of molten metal, and those currents generate electric currents through electromagnetic induction. The moving, electrically conductive liquid metal carries electrons with it, creating electrical currents that flow through the core. Those electrical currents, in turn, produce magnetic fields. It's an elegant self-sustaining system, a planetary dynamo driven by the slow crystallization of the inner core. The iron snow theory predicts a very specific structure for Mercury's core. At the center, a solid iron inner core, perhaps 600 to 800 kilometers in radius, made of pure crystalline iron. Surrounding that, a thick liquid outer core enriched with sulfur and possibly other light elements like silicon or oxygen, convecting vigorously as iron snow falls and sulfur-rich liquid rises, and possibly a thin stable layer at the very top of the outer core, where temperatures aren't quite high enough to maintain vigorous convection. This stable layer, if it exists, could be a few tens of kilometers thick, sitting between the convecting outer core and the rocky mantle above. Messenger's magnetic field measurements revealed another peculiarity that scientists are still working to explain. Mercury's field is highly asymmetric, significantly stronger in the northern hemisphere than in the southern. The field strength at the surface near Mercury's north pole is roughly 3 times stronger than at the south pole. On Earth, the magnetic field is relatively symmetric, with north and south magnetic poles of roughly equal strength. Sure, the field wanders and fluctuates, and the poles shift position over time, but the overall symmetry holds. Mercury's field appears to be fundamentally different, offset northward from the planet's center by about 480 kilometers. It's as if the dynamo generating the field is concentrated in the northern part of the core rather than at the planet's geometric center. This offset dipole configuration was completely unexpected. No other planet shows this pattern. Earth, Jupiter, Saturn, Uranus, Neptune. They all have magnetic fields that are roughly centered on the planet, even if the magnetic poles don't align exactly with the rotation poles. Mercury stands alone with this bizarre offset field. Why? What's different about Mercury's core that would produce such an asymmetric field? Computer simulations have attempted to reproduce this strange configuration. One successful model, published in the journal Nature Communications by researchers at the University of California, suggests that Mercury's mantle creates a thermal blanket effect. The thin rocky layer surrounding the core, only about 400 kilometers thick, might conduct heat away more efficiently from some regions than others. Maybe the mantle is thicker in some places, or has a different composition, or different mineral phases that conduct heat at different rates. These temperature variations at the core mantle boundary could force the convecting currents in the liquid outer core to organize themselves asymmetrically. If one hemisphere of the core is cooling faster than the other, the convection patterns would become lopsided. More vigorous convection in the rapidly cooling hemisphere would generate stronger magnetic fields there. Over time, this asymmetric convection would produce an offset dipole field, matching what Messenger observed. The model works mathematically, reproducing Mercury's field geometry quite well. But we don't yet know if it's correct. We need better measurements of the mantle structure and composition to test whether this thermal blanket effect is real. Another possibility involves the stable layer theory. If the top of the liquid outer core has indeed formed a non-convecting stable layer, as some models predict, this could suppress the dynamo in some regions while allowing it to operate at depth. Picture a layer of liquid metal at the top of the core that's stably stratified, like the layers in a parfait. In this layer, denser fluid sits below lighter fluid in a stable configuration. No convection happens here. It just sits there, conducting heat but not moving. Below this stable layer, vigorous convection continues, generating magnetic fields. But those fields have to pass through the stable layer to reach the surface. The stable layer filters and distorts them, suppressing some components while allowing others through. If the stable layer is thicker in the southern hemisphere than in the northern hemisphere, it would suppress the field more strongly in the south, producing the observed asymmetry. The interaction between Mercury's magnetic field and the solar wind creates additional complexity that makes the planet's magnetic environment one of the most dynamic and turbulent in the solar system. Mercury sits deep in the Sun's gravitational well, only 58 million kilometers away on average, where the solar wind is 3 times denser and moves 3 times faster than at Earth's orbit. The solar wind, that constant stream of charged particles flowing outward from the Sun's corona, consists mainly of electrons and protons racing through space at speeds of 300 to 800 kilometers per second. Near Mercury, these particles are even more energetic, compressed by the Sun's stronger gravity into a denser, faster flowing river of plasma. Despite its weakness, measuring only about 1% the strength of Earth's magnetic field at the surface, Mercury's field is strong enough to deflect this intense solar wind, carving out a miniature magnetosphere around the planet. A magnetosphere is the region of space dominated by a planet's magnetic field rather than the solar wind's magnetic field. It's like a protective bubble, though the shape is far from spherical. The solar wind compresses the magnetosphere on the sunward side, pushing it close to the planet's surface, while stretching it out into a long tail on the night side. But Mercury's magnetosphere is unlike Earth's in almost every way imaginable. It's tiny, extending only about 1.5 Mercury radii above the surface on the sunward side. For comparison, Earth's magnetosphere extends 10 Earth radii on the day side and hundreds of Earth radii on the night side. If you could see magnetospheres, Earth's would be a vast bubble many times larger than the planet itself. Mercury's would be a thin skin barely separating the planet from interplanetary space. The planet occupies a huge fraction of its own magnetosphere's volume, perhaps 40%. It's more like Mercury is wearing a tight-fitting jacket than sitting inside a protective bubble. Mercury's magnetosphere is also extraordinarily dynamic. Magnetic reconnection events, where magnetic field lines break and reconnect in new configurations, releasing enormous amounts of energy in the process, happen constantly. On Earth, major magnetic storms triggered by solar activity, the kind that produce spectacular auroras and can disrupt power grids and communications, might occur a few times per month during solar maximum. They're dramatic events that last for hours or days. On Mercury, the magnetosphere goes through complete reconfiguration cycles, what scientists call the Dungy cycle, after the physicist who first described it. Every 2 minutes, the whole system loads up with magnetic energy from the solar wind, reaches a breaking point, releases, that energy in a burst of reconnection and resets over and over again, hundreds of times each Earth day. Messenger observed what scientists call flux transfer events, temporary connections between Mercury's magnetic field and the interplanetary magnetic field carried by the solar wind. These events create something like magnetic tornadoes, twisting tubes of magnetic field lines that funnel solar wind particles directly down to Mercury's surface. Imagine a whirlwind made not of air, but of magnetic field lines, channeling high-energy electrons and protons from space down to the planet's surface. These magnetic tornadoes open and close continuously as the magnetosphere flexes and reconnects. They pump energy and particles into Mercury's exosphere, contributing to the processes that knock atoms loose from surface rocks. The weak magnetic field also means that Mercury's surface is bombarded by far more radiation than Earth's surface. Solar wind particles, galactic cosmic rays, and intense ultraviolet light from the nearby sun strike the planet's rocks directly, with only minimal shielding from the thin magnetosphere. This creates what's called space weathering, a suite of processes that alter the chemistry and appearance of surface materials over time. High-energy particles break chemical bonds in minerals. UV light heats the surface and drives photochemical reactions. Micrometeoroids vaporize on impact, creating tiny glass beads that darken the soil. Over billions of years, this relentless weathering has transformed Mercury's surface, darkening it, creating a veneer of altered material that obscures the original rock beneath. This intense space weathering is precisely what makes the discovery of hollows so remarkable. Because hollows look fresh, they appear bright against the darkened, weathered terrain around them. That brightness suggests they're young, that the processes forming them are removing the weathered material and exposing fresh rock beneath, or that volatile materials are escaping from hollows faster than space weathering can darken them. Either way, hollows represent active processes, things happening on Mercury's surface today, not ancient features left over from the planet's formation. This brings us to our second major mystery, one that's intimately connected to Mercury's volatile rich composition and its harsh surface environment. The presence of water ice and organic compounds in Mercury's polar regions, which we'll explore in detail shortly, and the strange features called hollows that appear to be forming on the planet's surface right now. We'll explore both of these interconnected phenomena because they reveal Mercury as a world far more volatile, rich, and geologically active than anyone expected before Messenger arrived. When Messenger first started returning high-resolution images of Mercury's surface, planetary geologists poring over the data noticed something peculiar. Scattered across certain regions of the planet, concentrated in impact craters and around volcanic features, were bright, irregular depressions, unlike anything seen elsewhere in the solar system. These features stood out immediately. They were small, typically ranging from tens of meters to a few kilometers in diameter, and shallow, only tens of meters deep. They had flat floors and bright walls, and they occurred in clusters, sometimes dozens or hundreds of them grouped together in what scientists started calling hollow fields. The hollows looked fresh. Their edges were crisp and sharp, not rounded and softened by billions of years of meteorite impacts and space weathering. Small craters from later impacts pockmarked the terrain around the hollows, but few, if any, of those craters formed on top of the hollows themselves. This age relationship, where one feature lacks impact craters that are common on adjacent terrain, tells geologists that the feature is young. If the hollows had been there for billions of years, they would have accumulated impact craters just like everything else. The fact that they haven't means they formed recently in geological terms. Most striking of all, the hollows appeared bright in Messenger's images, reflecting more sunlight than the dark, space-weathered terrain surrounding them. Mercury's surface is already quite dark, reflecting only about 12% of the sunlight that hits it, making it even darker than Earth's moon. The material in and around hollows is even darker in many places, yet the hollows themselves stand out as bright spots, patches of higher reflectance that catch the eye immediately when you look at the images. This brightness suggests the hollows expose fresh material that hasn't been darkened by space weathering yet, or that they're still actively forming, constantly removing weathered material and exposing bright stuff beneath. Hollows occur preferentially in what planetary scientists call low reflectance material, a type of dark rock that appears to be rich in carbon and other volatile elements. This low reflectance material, often abbreviated LRM, shows up in impact craters across Mercury's surface, particularly in the central peaks and walls where impacts have excavated material from depth and brought it up to the surface. It also appears around volcanic vents and in pyroclastic deposits, those explosive volcanic features where magma violently degassed and sprayed rock fragments across the landscape. The association between hollows and low reflectance material is strong and consistent. Where you find LRM, you often find hollows. Where hollows occur, there's almost always LRM nearby or beneath them. Messenger's instruments detected higher than expected concentrations of sulfur, potassium, sodium, and chlorine associated with the low reflectance material. The spacecraft's X-ray spectrometer and gamma-ray spectrometer could measure the abundance of these elements in surface rocks from orbit, and what they found surprised everyone. These are all relatively volatile elements, materials with low boiling points that shouldn't be abundant this close to the Sun. Mercury should be depleted in volatiles. That was one of the fundamental assumptions built into our models of inner solar system formation. The young Sun's heat should have driven these materials outward, leaving the inner planets, especially Mercury, with mostly refractory materials, stuff like iron and silicates that can withstand high temperatures. And yet here they are, concentrated in the darkest rocks on Mercury's surface, exactly where hollows form. Scientists believe hollows form through a process called sublimation, where solid material transforms directly into gas without passing through a liquid phase. We see this on Earth in certain conditions. Ice can sublimate in very dry air, which is why ice cubes shrink in your freezer over time, even though they never melt. Carbon dioxide ice, dry ice, sublimates readily at atmospheric pressure, turning directly from solid to gas. On Mercury, with its virtually non-existent atmosphere, even less volatile materials can sublimate if exposed to intense solar radiation, or if they're chemically unstable in the harsh surface environment. The leading hypothesis is that hollows form when volatile-bearing minerals in the low reflectance material are exposed to space weathering processes. The intense solar wind bombardment, the ultraviolet radiation from the nearby Sun, and the extreme temperature variations that swing 600 degrees between day and night all work together to break down these minerals. The chemical bonds holding the volatile compounds in the crystal structure break apart. The volatile elements, now freed from the mineral lattice, escape into Mercury's tenuous exosphere as gas molecules or individual atoms. As the volatiles escape, they leave behind pits and depressions, the hollows we see on the surface. But which volatile compounds are responsible? What exactly is sublimating away to create these features? Several candidates have been proposed, and the answer is probably some combination of multiple compounds rather than a single material. Sulfur compounds head the list of likely culprits. Magnesium sulfide and calcium sulfide are both relatively volatile for minerals, meaning they can break down and release sulfur gas under the right conditions, and they're plausible components of Mercury's low reflectance material, given the high sulfur concentrations Messenger detected. Laboratory experiments have shown that sulfide minerals can decompose when bombarded by high-energy ions similar to those in the solar wind, releasing sulfur atoms that would immediately escape into space from Mercury's surface. Messenger detected spectroscopic signatures consistent with sulfides in regions where hollows occur. Different minerals absorb and reflect light at different wavelengths, creating a unique spectral fingerprint. By analyzing the spectrum of light reflected from Mercury's surface, scientists can identify which minerals are present. The spectra from hollow regions show features that match sulfide minerals, supporting the idea that these compounds play a role in hollow formation. The sulfides aren't the hollows themselves. They're what was there before the hollows formed. As the sulfides break down and release sulfur, they leave behind altered minerals and empty space, creating the depressions we call hollows. Carbon is another strong possibility. Graphite, a form of pure carbon, appears to be common in Mercury's low reflectance material. Messenger's spectrometers detected strong carbon signatures in the darkest regions of the surface. Some scientists estimate that the LRM contains up to a few weight% carbon, which is extremely high for a rocky planet this close to the Sun. Where did all this carbon come from? It might be primordial, incorporated into Mercury when the planet formed, or it could have been delivered later by carbonaceous asteroids and comets impacting the surface over billions of years. Either way, it's there, and it might be escaping. Under bombardment by solar wind protons, graphite could be chemically converted to methane gas. This is a known reaction. Hydrogen from the solar wind reacts with carbon on the surface, forming CH4 molecules that would immediately escape into space from Mercury. Over millions of years, this process could remove significant amounts of carbon, excavating pits where graphite-rich material used to be. The rate of removal would depend on how much carbon is present and how exposed it is to the solar wind, which might explain why hollows cluster in certain regions but not others. Chlorides have also been proposed. Sodium chloride, common table salt, has been detected in Mercury's exosphere, blasted off the surface by micrometeorite impacts. The detection of sodium and chlorine atoms in the exosphere tells us these elements exist on the surface in some form, probably as chloride minerals. If concentrated in subsurface deposits, chloride minerals exposed by impacts or volcanic activity could sublimate when brought to the surface. Chlorides are more volatile than silicate minerals, able to evaporate at lower temperatures. Under Mercury's harsh conditions, with daytime temperatures exceeding 400 degrees Celsius and constant bombardment by solar radiation, exposed chloride deposits might slowly evaporate away, creating hollows in the process. Whatever the exact composition, the hollows tell us something profound about Mercury. The planet contains far more volatile elements than our models of solar system formation predict. These volatiles aren't just trace contaminants. They're abundant enough to create features visible from orbit, scattered across substantial fractions of the planet's surface. They're buried throughout the crust, hidden in dark, low reflectance material, waiting to be exposed by impacts or volcanic activity. Once exposed, they begin to sublime, creating hollows that expand and deepen over time. The rate of hollow formation appears to be quite rapid on geological timescales. Scientists have estimated the rate by comparing the depth of hollows to estimates of how fast materials can sublime under Mercury's conditions. The calculations suggest that hollows could grow at rates of tens of centimeters per million years. That might sound slow, and by human standards it certainly is. But for geological processes, it's remarkably fast. For features only tens of meters deep, this growth rate means individual hollows could form in less than 100 million years. Some may be much younger than that, possibly only a few million years old. Some might even be actively forming today, deepening and expanding as we speak. The distribution of hollows provides clues about Mercury's geological history and the processes driving hollow formation. MESSENGER mapped more than 440 distinct groups of hollows during its mission, though this is certainly an undercount limited by the resolution of the images. Higher resolution observations would undoubtedly reveal many more smaller hollows. The hollows are concentrated near the hot poles, those longitudes on Mercury's equator that receive the most intense solar radiation due to the planet's elliptical orbit and peculiar rotation. This concentration suggests that solar heating plays a role in driving the sublimation process. More heat means faster chemical breakdown, faster sublimation, more hollow formation. Hollows also tend to occur on equator-facing slopes, where sunlight strikes more directly and surface temperatures are higher. A crater wall tilted toward the equator receives more direct sunlight and heats up more than a pole-facing slope. The equator-facing slopes show more hollows, supporting the idea that temperature matters. And yet, hollows are found at all longitudes, including some impermanently shadowed regions where sunlight never reaches directly. This indicates that solar heating isn't the only factor. Space weathering from the solar wind and high-energy radiation may contribute even in shadowed areas where temperatures stay low. The presence of hollows in volcanic regions provides particularly strong evidence for volcanic outgassing in Mercury's history. Mercury's volcanism, long suspected but confirmed definitively by MESSENGER, appears to have brought volatile rich material from the interior to the surface. Vast plains of smooth volcanic rock cover much of the northern hemisphere, evidence of massive lava flows that flooded the lowlands billions of years ago. These aren't the dramatic shield volcanoes we see on Earth or Mars. Mercury's volcanic features are more subtle, mostly broad plains of frozen lava with few obvious vents or cones. But MESSENGER also discovered evidence for explosive volcanism, the kind driven by gas pressure rather than just flowing lava. Pyroclastic deposits, layers of rock fragments sprayed across the surface by violent eruptions, surround certain volcanic vents. The largest of these, called Nathera Facula, is a massive explosive volcanic deposit more than 300 kilometers in diameter. At its center lies a volcanic vent about 40 kilometers across that has been the site of at least 3 major explosive eruptions. These eruptions required volatiles, gases dissolved in the magma that expand explosively when the pressure drops as the magma rises toward the surface. Where did those volatiles come from? They must have been present in Mercury's interior, dissolved in the magma at depth. As the magma rose and the pressure decreased, the volatiles came out of solution like bubbles forming in a bottle of soda when you open the cap. The expanding gases shattered the magma into tiny fragments and blasted them across the landscape. After the eruptions, the volatile-rich rock settled to the surface as pyroclastic deposits. And now, Billions of years later, those deposits are host to some of Mercury's most spectacular hollow fields. The volcanic connection tells us that Mercury's mantle contains more volatiles than we thought. It's not just the surface that's volatile rich. There are reservoirs of sulfur, carbon, and other volatile elements deep inside the planet, incorporated when Mercury formed and never fully outgassed. When volcanic activity brings this material to the surface, it exposes these volatiles to the harsh surface environment, where they begin to escape, creating hollows. MESSENGER identified over 440 groups of hollows across Mercury's surface during its 4-year mission. That's a conservative count, limited by the resolution of the images and the coverage of the planet. Many hollows are small, only tens of meters across, right at the limit of what MESSENGER's cameras could resolve from orbit. Higher resolution observations will undoubtedly reveal many more. Each group might contain dozens or even hundreds of individual hollows clustered together, meaning the total number of hollow features on Mercury probably numbers in the tens of thousands at minimum. The Bepi-Colombo mission, currently en route to Mercury and scheduled to arrive in November 2026, will provide much higher resolution imagery than MESSENGER achieved. Bepi-Colombo's cameras can resolve features down to a few meters across under optimal conditions, compared to MESSENGER's best resolution of a few tens of meters. This order of magnitude improvement should reveal countless additional hollows that were simply too small for MESSENGER to detect. Bepi-Colombo may even be able to measure whether hollows are still growing today by comparing its images with those from MESSENGER taken a decade and a half earlier. If the hollows have expanded even slightly, if their boundaries have shifted outward by even a few meters, it would confirm that this process is ongoing, that Mercury's surface is still actively evolving through volatile loss. The hollows also have profound implications for understanding Mercury's formation. The volatiles creating these features had to be incorporated into Mercury's crust when the planet formed or delivered shortly thereafter. This means Mercury didn't lose all its volatile elements during formation, despite its proximity to the Sun and despite the young Sun's energetic output. The planet managed to accumulate and retain sulfur, carbon, chlorine, and other volatiles that conventional models said shouldn't be there. Perhaps the planet formed farther out in the solar system, beyond the region where volatiles were completely depleted, and then migrated inward through gravitational interactions with other forming planets. Planetary migration is a common feature of modern solar system formation models. Jupiter and Saturn almost certainly migrated from where they formed, and their migration would have sent countless planetesimals and embryonic planets careening through the inner solar system. Maybe Mercury started farther out and ended up close to the Sun through this cosmic game of billiards. Or maybe the early solar nebula was more heterogeneous than we thought, with pockets of volatile-rich material surviving even close to the Sun. The nebula wasn't a uniform cloud. It had structure, turbulence, density variations. Perhaps some of these variations allowed volatile-bearing materials to accumulate locally and form Mercury's building blocks despite the Sun's heat. This would require rethinking our models of how the solar nebula mixed and homogenized in the early solar system. The discovery of hollows fundamentally changed how planetary scientists think about Mercury. This is not a simple inert ball of rock and iron. It's a world with a complex chemical inventory that includes abundant volatiles, ongoing surface processes that are actively modifying the landscape, and a geological history that we're only beginning to understand. The hollows represent the present-day endpoint of processes that began billions of years ago when Mercury formed and incorporated volatile bearing materials into its structure. They're windows into the planet's composition, revealing materials that would otherwise remain hidden beneath a veneer of space-weathered rock. But hollows are not the only evidence for volatiles on Mercury. The planet's polar regions harbour an even more surprising discovery, one that seems to defy all logic given Mercury's proximity to the Sun. Water ice, actual frozen water, the same stuff that makes up glaciers on Earth and polar caps on Mars, existing in permanent shadow at the poles of the solar system's hottest planet. The discovery of water ice on Mercury ranks among the most counterintuitive findings in the history of planetary exploration. And the story of how we found it, confirmed it, and came to understand how it got there reveals the remarkable power of scientific observation and reasoning. Mercury's axis of rotation is tilted by less than 1 degree relative to its orbital plane. Earth's axis tilts at 23.5 degrees, giving us our seasons as different hemispheres lean toward or away from the Sun over the course of the year. Mars tilts at 25 degrees. Even Jupiter, a gas giant, manages a tilt of about 3 degrees. Mercury's axis is essentially perpendicular to its orbital plane, more upright than any other planet in the solar system by a significant margin. This upright orientation has a profound consequence for Mercury's polar regions. Because the axis has virtually no tilt, the Sun never rises more than a degree above the horizon at the poles. If you stood at Mercury's north or south pole, you'd see the Sun skim along the horizon, never climbing into the sky, circling endlessly, but never providing direct overhead illumination. Impact craters near the poles, especially those with high walls and deep floors, cast permanent shadows. The Sun never illuminates the interiors of these craters. They remain in perpetual darkness, year after year, century after century, eon after eon, never once seeing direct sunlight since the moment they formed. Without sunlight, these permanently shadowed regions never warm up. While Mercury's equatorial regions bake at temperatures exceeding 400 degrees Celsius during the long Mercurian day, turning lead into liquid and making the surface glow dull red, the floors of these polar craters remain at temperatures below -200 degrees Celsius. That's colder than liquid nitrogen, colder than the surface of Jupiter's icy moon Europa, cold enough to trap water ice for billions of years without any loss to sublimation. In these pockets of eternal darkness, ice can survive and accumulate over geological time, preserved like specimens in a cosmic freezer. In 1991, a team of astronomers led by John Harmon used the Arecibo radio telescope in Puerto Rico to bounce radar signals off Mercury's poles. Arecibo, with its 300-meter dish carved into the Puerto Rican hills, was the most powerful radio telescope in the world at the time. When they analyzed the returning radar echoes, they detected something strange and unexpected. Certain regions near both poles reflected the radar in a highly distinctive way. Bright radar echoes, much brighter than the surrounding terrain, with a particular polarization signature. The pattern of reflection matched precisely what you'd expect from pure water ice. The ice would reflect radar waves very efficiently, and it would reverse the polarization in a characteristic way. The discovery was immediately controversial. Water ice on Mercury, the planet closest to the Sun, where daytime temperatures can melt lead. It seemed absurd, a result so counterintuitive that many scientists assumed there must be another explanation. Skeptics suggested the radar bright spots might be deposits of sulfur, which can also reflect radar efficiently, or metal sulfides, or some exotic mineral that just happened to reflect radar waves similarly to ice. The debate continued for years, with observations from other radio telescopes confirming the existence of radar-bright regions, but unable to definitively prove they were water ice. The problem was that radar observations from Earth could only tell us that something reflective was there. They couldn't directly measure composition. They couldn't measure temperature or look at the features in visible light or detect hydrogen, the telltale signature of water. For 2 decades, the question remained tantalizingly unresolved. Water ice on Mercury was possible, allowed by the physics of permanently shadowed craters, but not proven. Many scientists suspected it was there, but suspicion isn't the same as confirmation. We needed a spacecraft at Mercury with instruments designed to detect ice directly. Then Messenger arrived, and over the course of its 4-year orbital mission, it settled the debate conclusively. Using 3 independent lines of evidence, 3 completely different measurement techniques that all pointed to the same conclusion, Messenger confirmed beyond any reasonable doubt that Mercury's polar deposits consist primarily of water ice. The convergence of evidence was overwhelming, leaving no room for alternative explanations. First, Messenger's neutron spectrometer measured the abundance of hydrogen near the poles. This instrument works by detecting neutrons produced when galactic cosmic rays, high-energy particles from outside the solar system, strike Mercury's surface. When a cosmic ray hits an atomic nucleus in the surface rocks, it can knock out neutrons. These neutrons then bounce around in the upper few tens of centimeters of soil before either being absorbed by another nucleus or escaping back into space where the detector can count them. The way these neutrons scatter and slow down depends critically on what elements are present in the rocks. Hydrogen is particularly effective at slowing down neutrons because hydrogen nuclei, protons, have about the same mass as neutrons. When a fast neutron collides with a proton, it can transfer most of its energy in a single collision, like 2 billiard balls hitting head-on. Messenger detected a strong suppression of fast neutrons over the polar regions, exactly what you'd expect if there was abundant hydrogen present. The only plausible source of so much hydrogen in Mercury's polar craters is water ice. H2O, 2 hydrogen atoms bound to 1 oxygen atom. The hydrogen signal was concentrated in the same regions where the radar had shown bright reflections decades earlier. The correlation was striking. Every radar-bright region showed elevated hydrogen. Every hydrogen-rich region corresponded to a radar bright spot. The 2 independent measurements, made with completely different techniques, pointed to the same locations and the same conclusion. Second, Messenger's laser altimeter measured the reflectance of the polar regions at near-infrared wavelengths. This instrument, designed primarily to measure Mercury's topography by bouncing laser pulses off the surface and timing how long they take to return, could also measure how much of the laser light was reflected back. Different materials reflect infrared light differently. Fresh, clean water ice is highly reflective in the near-infrared. Space-weathered rock is dark. The optically bright regions detected by the laser altimeter match the radar-bright regions and the hydrogen-rich regions. All 3 measurements pointed to the same locations. The correlation was so strong it couldn't be coincidence. Third, Messenger created detailed temperature maps of the polar regions using the actual topography measured by the laser altimeter. Scientists built computer models that calculated the temperature at every point near the poles, accounting for the height of crater walls, the angle of slopes, and how sunlight heats the surface. These models showed that the locations of the radar-bright, hydrogen-rich, optically bright deposits coincided precisely with regions cold enough for water ice to remain stable over billions of years. The correlation was remarkable. Everywhere the temperature stayed below minus 170 degrees Celsius year-round, MESSENGER found evidence of ice. Where temperatures crept slightly higher, the ice disappeared or became buried. The measurements revealed something else crucial. The ice wasn't always exposed at the surface. In the coldest regions, where temperatures never rose above minus 200 degrees Celsius, the ice appeared to sit right at the surface or very close to it, mixed with or covered by only a thin layer of darker material. In slightly warmer regions, where temperatures range between minus 170 and minus 150 degrees Celsius, the ice was buried under 10 to 20 centimeters of dark insulating material. This layering makes perfect sense. Where it's cold enough, ice can exist at the surface. Where it's slightly warmer, the ice would sublimate if exposed, so it can only survive if buried under an insulating blanket. This dark layer covering much of the ice is believed to be complex organic compounds, carbon-based molecules delivered to Mercury by the same comets and asteroids that brought the water. When icy bodies impact Mercury, they don't just deliver water. They also contain organic materials, the tarry, carbon-rich compounds found in carbonaceous chondrite meteorites. Over billions of years, as countless comets and asteroids struck Mercury, they deposited both water and organics at the poles. The water froze in the permanently shadowed craters. The organics mixed with it or formed a layer on top. Exposure to radiation over eons has darkened these organics further, cooking them with cosmic rays and solar particles until they turn nearly black, creating a layer that absorbs what little light reaches into the shadowed craters while insulating the ice below. The total amount of water ice trapped in Mercury's polar craters is staggering. Scientists estimate between 100 billion and 1 trillion metric tons of water ice on Mercury's surface. The uncertainty in this estimate comes from not knowing exactly how thick the ice deposits are and how much of the shadowed area they cover. But even the low-end estimate is enormous. 100 billion tons of water. To put that in perspective, that's enough water to fill a cube more than 450 meters on each side. If you spread it over an area the size of Washington, D.C., the ice would be more than 2 miles thick, over 3 kilometers deep. Where did all this water come from? The most likely source is impacts from comets and water-rich asteroids over billions of years. Comets are essentially dirty snowballs, mixtures of ice and rock from the outer solar system. When a comet strikes Mercury, the impact vaporizes the ice instantly. Most of those water molecules escape into space, broken apart by sunlight or swept away by the solar wind before they can settle anywhere. But a tiny fraction, perhaps 1 in 10,000 water molecules, find their way to the poles through a process called ballistic hopping. When water molecules vaporize on Mercury's sunlit surface, they don't stay put. With virtually no atmosphere to slow them down or scatter them, they leap in ballistic arcs, following parabolic trajectories like tiny spacecraft in orbit. A water molecule vaporized at the equator might arc hundreds of kilometers through space before landing again. Most of these molecules land back on the hot surface and vaporize again, repeating the process. But some land in shadowed regions where the temperature is too low for them to escape. Once a water molecule lands in a permanently shadowed crater where the temperature stays below minus 170 degrees Celsius, it freezes and stays frozen. It's trapped. Over billions of years, this process accumulates ice, Impact after impact delivers water. Most escapes, but a small fraction gets trapped at the poles. The ice builds up slowly, layer by layer, perhaps only micrometers per year on average. But over 4 billion years, that adds up to deposits meters or even tens of meters thick in some craters. The process continues today. Comets and asteroids still strike Mercury occasionally, still deliver water, still feed the polar ice deposits. The ice we see is a mixture of ancient ice deposited billions of years ago and relatively fresh ice delivered by recent impacts. Recent research has identified another potential source of water on Mercury, a mechanism that operates continuously rather than depending on sporadic impacts. The planet's surface rocks contain significant amounts of hydrogen, bonded to oxygen atoms in mineral structures, forming what chemists call hydroxyl groups. These OH groups are common in many minerals. When protons from the solar wind, bare hydrogen nuclei streaming out from the sun, strike Mercury's surface, they can combine with these hydroxyl groups to form water molecules. A solar wind proton hits an OH group in a surface mineral, combines with it, and creates H2O. This newly formed water molecule then behaves like any other water molecule on Mercury's surface. It vaporizes, begins ballistic hopping, and potentially makes its way to the polar cold traps where it freezes. Computer models of this process suggest it could account for about 10% of Mercury's polar ice, with the remaining 90% coming from comets and asteroids. 10% might not sound like much, but it means that Mercury is actively making water right now, every second, as solar wind protons rain down on the surface. The planet isn't just a passive repository for ice delivered from elsewhere. It's chemically generating water through reactions between the solar wind and surface minerals, a process that's been operating continuously for billions of years and continues today. The presence of water ice at Mercury's poles has profound implications for understanding the delivery of water throughout the inner solar system. If water can survive at Mercury, in the most hostile environment imaginable for ice, exposed to more solar radiation than anywhere else in the inner solar system, then water delivery to Earth, Mars, and Venus was probably far more efficient than we previously thought. The same comets and asteroids that delivered water to Mercury also delivered water to the other terrestrial planets. If Mercury managed to accumulate and retain hundreds of billions of tons despite its harsh conditions, Earth must have received vastly more. This ice also provides a remarkable record of cometary impacts spanning billions of years. By analyzing the ice's composition and the organic materials mixed with it, future missions might be able to reconstruct the history of volatile delivery to the inner solar system. Different comets have slightly different isotopic compositions, different ratios of deuterium to hydrogen, different abundances of trace elements. These variations act like fingerprints. If we could drill into Mercury's ice deposits and analyze ice from different depths, from different time periods in the planet's history, we could trace how the population of comets bombarding the inner solar system changed over time. And it presents a tantalizing possibility for future human exploration. Mercury's polar ice could provide water and hydrogen fuel for spacecraft, making the planet a potential waypoint for missions venturing deeper into the inner solar system or out to the asteroid belt. Water is incredibly valuable in space. You can drink it, use it for radiation shielding, extract oxygen from it for breathing, split it into hydrogen and oxygen for rocket fuel. Finding hundreds of billions of tons of it on Mercury, in a location where solar panels would work incredibly well, makes the planet suddenly much more interesting from an exploration and utilization perspective. But the ice deposits, as remarkable as they are, represent only part of the volatile story on Mercury. We've talked about the hollows, those mysterious depressions forming where volatile minerals sublime away. We've discussed the ice hidden in eternal shadow at the poles. Now we need to address the third piece of evidence for ongoing geological activity on Mercury, the feature that proves most conclusively that this planet is still geologically alive. The surface bears the marks of global contraction, a slow but inexorable shrinking as the interior cools and the whole planet decreases in volume. And recent discoveries have revealed that this contraction is still happening today, making Mercury one of only 2 tectonically active planets in the solar system. The basic physics is straightforward. As a planet cools, it shrinks. When molten rock solidifies, it occupies less volume than when it was liquid. When metal cools, it contracts. These aren't exotic effects. They're fundamental material properties. As Mercury's enormous iron core slowly loses heat to space, radiating away the warmth accumulated during the planet's formation 4.5 billion years ago, the core's temperature drops. As it cools, it contracts. The solid inner core grows as iron crystallizes from the liquid outer core. The liquid outer core shrinks as it cools and as material is removed to build the inner core. The whole interior of the planet becomes smaller. The rocky crust and mantle at the surface, locked in place and unable to shrink smoothly, must accommodate this interior contraction somehow. They do so by cracking and folding, with one section of crust being thrust up and over an adjacent section along low-angle faults. This creates cliff-like features called lobate scarps, from the Latin lobatus meaning having lobes or curved, and scarpus meaning cliff or steep slope. These aren't like the fault scarps you might see on Earth, where vertical cliffs form along strike-slip faults. Mercury's scarps are thrust faults with gently curved cliff faces rising from surrounding plains. When NASA's Mariner 10 spacecraft flew past Mercury in March and September 1974, and again in March 1975, photographing less than half the planet's surface during 3 brief encounters, it revealed enormous fault scarps snaking across the landscape. These weren't small features. The largest scarps visible in Mariner 10's images were hundreds of kilometers long and more than 2 kilometers high. Discovery Rupes, one of the first scarps identified and studied, extends for at least 450 kilometers across the surface. Its cliff face rises more than 1.5 kilometers above the surrounding plains, a towering wall of rock cutting across ancient cratered terrain. Enterprise Rupes, the largest known fault scarp on Mercury, stretches for approximately 1,000 kilometers, comparable in length to California's San Andreas Fault, and creates a cliff face with over 3 kilometers of relief. If you stood at the base of Enterprise Rupes and looked up, the cliff would rise above you higher than many mountain ranges on Earth, a tremendous wall cutting across Mercury's cratered face. Unlike Earth's San Andreas Fault, which is a strike-slip fault where 2 plates slide past each other horizontally, Mercury's lobate scarps are thrust faults. One section of crust has been pushed up and over another section, riding up along a fault plane that dips at a shallow angle into the crust. The geometry tells us these scarps formed under compression as the planet's shrinking diameter forced crustal blocks together like ice floes crumpling as a frozen lake contracts. Mariner 10's images showed scarps in the limited region it photographed, but couldn't confirm whether these features existed globally or were confined to specific areas. The spacecraft might have just happened to image a particularly scarp-heavy region of the planet. For 3 decades, That question remained unanswered, one of many mysteries about Mercury that could only be resolved by a dedicated orbital mission. When Messenger entered orbit in March 2011, one of its primary objectives was to map the entire planet at high resolution and determine whether Lobat scarps occurred everywhere or just in isolated regions. The answer came quickly and decisively. Lobat scarps are found at all latitudes and all longitudes on Mercury. From the equator to the poles, in both eastern and western hemispheres, across ancient heavily cratered terrain and younger volcanic plains, across highlands and lowlands, the scarps are ubiquitous. Every region of the planet's surface bears the unmistakable marks of global shrinkage. Messenger confirmed beyond any doubt that Mercury experienced comprehensive, planet-wide contraction. By carefully measuring the length and height of all the major scarps visible in Messenger's images, and using the geometry of thrust faulting to calculate how much horizontal distance was shortened to create each scarp's vertical relief, planetary scientists can estimate how much Mercury has contracted overall. Each scarp represents a certain amount of crustal shortening. The amount depends on the scarp's height and the angle of the underlying fault. Add up all the scarps, account for the ones too small to see or that have been obscured by later impacts and volcanic flows. Apply statistical methods to estimate global coverage, and you can calculate the total change in Mercury's radius. The numbers tell a remarkable story. Mercury's radius has decreased by somewhere between 4 and 14 kilometers over the planet's history. That's the range of current estimates, with most scientists favoring a value around 7 kilometers, based on detailed mapping of scarp distributions and fault geometries. Think about what that means. The planet's entire radius has shrunk by 7 kilometers. The diameter has decreased by 14 kilometers. The circumference at Mercury's equator has decreased by about 44 kilometers. Walk all the way around Mercury's equator today, and you travel 44 kilometers less than if you'd made the same journey 4 billion years ago, when the planet first solidified. This contraction has profound implications for understanding Mercury's thermal history and the evolution of its interior. To contract this much, the planet must have lost an enormous amount of internal heat over billions of years. Computer models of Mercury's thermal evolution, sophisticated simulations that track how heat flows from the core through the mantle to the surface and radiates into space, attempt to match this observed contraction with predictions of how quickly the core should cool, given Mercury's size and composition. The results from these models are intriguing and somewhat puzzling. The rate of cooling implied by the 7-kilometer contraction is actually slower than the models initially predicted for a planet of Mercury's size. A small planet should cool quickly, radiating heat efficiently because of its large surface area to volume ratio. The models suggested Mercury should have cooled faster and contracted more than we observe. The fact that it hasn't contracted quite as much as expected tells us something about the planet's interior structure, though exactly what remains debated. Perhaps the core contains more heat-producing radioactive elements than we thought. Perhaps the mantle provides more insulation than the models assumed. Perhaps the sulfur in the core lowers its thermal conductivity, slowing heat loss. All of these possibilities are being explored. But here's the intriguing part that transformed our understanding in recent years. If Mercury has been contracting, it's still losing heat. If it's still losing heat, the core is still cooling. And if the core is still cooling, actively dropping in temperature right now, then the contraction should still be happening. The planet should still be shrinking today. For decades after Mariner 10's discoveries, Scientists assumed that Mercury's large-scale contraction ended billions of years ago. The thinking was straightforward. The big lobate scarps like Enterprise Rupers and Discovery Rupes formed early in the planet's history, when cooling and contraction rates were high. As the planet's heat loss slowed over time, the rate of contraction decreased. Eventually, billions of years ago, the contraction rate dropped so low that no new scarps formed. The planet became essentially dormant, its interior settling into a state of slow, quiet cooling that no longer produced visible tectonic features. Mercury, in this view, was tectonically dead, a planet whose active geological history ended in the ancient past. Then, in 2016, a team of planetary scientists led by Thomas Waters at the Smithsonian Institution's National Air and Space Museum published a discovery in the journal Nature Geoscience that changed everything we thought we knew about Mercury's current state. During the final phases of the Messenger mission, as the spacecraft's fuel dwindled and mission controllers knew the end was approaching, they made a crucial decision. Rather than keeping the spacecraft in its nominal mapping orbit for as long as possible, they allowed the orbit to decay naturally, letting Mercury's gravity pull the spacecraft lower and lower. This low-altitude campaign brought Messenger much closer to Mercury's surface than it had been during the primary mission. The spacecraft dipped to altitudes as low as 15 kilometers above the surface in its final weeks, compared to the hundreds of kilometers altitude during normal mapping operations. This dramatic decrease in altitude produced images with extraordinary resolution, revealing surface details only tens of meters across, sometimes even smaller in the very best images. Waters and his team pored over these high-resolution images systematically, searching for small-scale tectonic features that would have been invisible in the lower-resolution images from earlier in the mission. What they found was absolutely stunning and completely unexpected. Tiny fault scarps, only kilometers long and tens of meters high, scattered across the northern hemisphere where the best low-altitude coverage existed. These small scarps were orders of magnitude smaller than the giant Lobate scarps, known from Mariner 10 and Messenger's earlier images. A typical small scarp might be only 5 kilometers long, with a cliff face 50 meters high. Compare that to Enterprise Rupes at 1,000 kilometers long and 3,000 meters high. The small scarps are 200 times shorter and 60 times less tall. They're tiny features, barely noticeable unless you're looking carefully at high-resolution images, but their small size is precisely what makes them so significant. Small surface features don't survive long on Mercury or any airless body in the solar system. Meteorite impacts constantly bombard the surface. Over time, these impacts gradually erode and fill in topographic relief. A small scarp, only tens of meters high, would be completely erased by impacts in a geologically short time. Every impact that hits near the scarp throws out debris that partly buries the cliff. Every impact on the scarp itself chips away at the cliff face. Over tens or hundreds of millions of years, the scarp would be degraded beyond recognition, smoothed out and buried, until it was indistinguishable from the surrounding terrain. The fact that these scarps exist and show crisp, well-defined cliff faces with sharp boundaries means they must be young. Very young, geologically recent. By comparing the degradation state of Mercury's small scarps to similar features on the Moon, where we have better age constraints from samples returned by Apollo missions and from crater counting techniques, scientists estimate Mercury's small scarps are less than 50 million years old. Probably much younger than that, possibly only a few million years old, for the freshest looking examples. 50 million years might sound like a long time by human standards, and it certainly is. But in planetary geology, where we routinely discuss events that happened billions of years ago, 50 million years is incredibly recent. Earth is 4.5 billion years old. 50 million years is about 1% of that age. It's roughly the time since the asteroid impact that killed the dinosaurs. Finding tectonic features on Mercury that formed within the last 50 million years is like finding features that formed yesterday on a planetary timescale. Some of the small scarps show another telling feature that confirms their tectonic origin and provides additional age constraints. Narrow troughs, called graben in geological terminology, incised into the top of the scarp itself. These graben form through a specific process. When a thrust fault pushes one block of crust up and over another, creating a scarp, the top of the uplifted block experiences extensional stress. Picture bending a piece of wood. The inner curve is compressed, the outer curve is stretched and under tension. The same thing happens with Mercury's crust when it's thrust upward. The crest of the ridge is stretched and cracks, forming normal faults that create narrow troughs. The presence of graben confirms that the scarps are tectonic features formed by thrust faulting, rather than some other process like landslides or differential compaction. And because graben are even more fragile than scarps, even more susceptible to being filled in by impact debris, their presence indicates extremely young ages. While graben only a few meters deep would be filled in by meteorite ejecta in just a few million years under Mercury's bombardment rate, the distribution of small scarps provides additional evidence for recent activity. They cluster in certain regions, particularly in the northern hemisphere, where MESSENGER's final low-altitude images had the best resolution. But even accounting for this observational bias, the distribution is non-random. Many of the small scarps occur near larger, older lobate scarps, often aligned parallel to the ancient structures. This suggests that the same fault systems that produced the giant scarps billions of years ago are still active today. They're not slipping as dramatically as they once did. Instead of producing kilometer-high cliffs, the modern faulting produces scarps only tens of meters high. But the key point is they're still active, still moving, still accommodating ongoing contraction. This makes perfect sense if Mercury's cooling rate has decreased over time. In the early solar system, Mercury's interior was much hotter, perhaps 1500 degrees Celsius hotter than today. Heat flowed outward more rapidly because of the stronger temperature gradient between the hot interior and the cold surface. The planet contracted more quickly, producing large scarps. As the interior cooled and the temperature difference decreased, the cooling rate slowed. The contraction rate decreased proportionally. Today, Mercury continues to cool and contract, just more slowly than in the past. The modern contraction produces small scarps rather than large ones, but it's still happening, still measurably changing the planet's size. In 2023, another study provided even more dramatic evidence for recent and ongoing tectonism. Benjamin Mann, a doctoral student at the Open University in the United Kingdom, working under the supervision of Professor David Rothery, conducted a meticulous global survey of MESSENGER images looking for even smaller features called graben. Mann wasn't looking for the graben associated with small scarps. He was looking for graben that formed on top of the large ancient lobate scarps themselves. Here's why this matters. When a lobate scarp forms billions of years ago through thrust faulting, it creates a ridge rising above the surrounding plains. That ridge sits there for eons, slowly being degraded by impacts. But if that same underlying fault becomes active again later, if it slips again and thrusts the crust upward a bit more, it lifts the ancient ridge higher. As the ridge is lifted, the top of the ridge experiences extensional stress, just like when the ridge first formed. This extension cracks the crust along the scarp's crest, forming new small graben. The presence of these graben on top of ancient Labat scarps indicates that those scarps have experienced recent reactivation. The faults didn't just move billions of years ago. They moved again relatively recently, perhaps within the last few 100 million years, perhaps much more recently. Man identified hundreds of these graben across Mercury's surface in his systematic survey, often in sets clustered along the crests of major scarps. Many of these graben are quite small, only tens of meters wide and a few meters deep, which means they're young by the same logic we applied to the small scarps. The same meteorite bombardment that erodes small scarps also fills in small graben. Their survival indicates formation within the last few 100 million years at most. The discovery of so many young graben scattered across Mercury's surface demonstrates that the contraction isn't confined to one or two isolated regions where some local process might be at work. It's global. Across the entire planet, ancient fault systems are still active, still slipping occasionally, still accommodating the shrinkage as Mercury's massive iron core continues its slow cooling toward equilibrium with the surrounding space. This makes Mercury one of only two tectonically active rocky planets in the solar system that we know of. Earth, of course, is the other tectonically active planet. Earth's plate tectonics, driven by mantle convection and the cooling of the planet's interior, creates earthquakes, builds mountains, opens ocean basins, and constantly reshapes the surface. But Earth's tectonics operates through a completely different mechanism. Earth has multiple tectonic plates, pieces of lithosphere that move relative to each other. Plates converge at subduction zones where one plate slides beneath another. They diverge at mid-ocean ridges where new crust forms. They slide past each other at transform faults. This plate tectonic system is unique to Earth among the rocky planets in our solar system. Mercury doesn't have plate tectonics. Its lithosphere, the rigid outer shell comprising the crust and uppermost mantle, appears to be a single unbroken plate covering the entire planet. There are no subduction zones, no mid-ocean ridges, no evidence for the kind of horizontal plate motions we see on Earth. But Mercury does have active tectonics of a different kind, what planetary scientists call one-plate tectonics. The single lithospheric shell is breaking and deforming in response to the shrinking interior, creating a global network of thrust faults and fold structures all driven by planetary contraction. And where there's active tectonic activity, there's almost certainly seismic activity. On Earth, when rock suddenly slips along a fault during an earthquake, it generates seismic waves that propagate through the planet's interior and along its surface. The same physics must apply to Mercury. When one of those thrust faults slips, accommodating another few centimeters or meters of contraction in a sudden rupture, it should produce Mercury quakes, seismic waves that travel through Mercury's interior. We've never directly detected Mercury quakes because we've never placed seismometers on Mercury's surface. Seismology requires instruments sitting on the ground, feeling the vibrations as they pass. Orbital spacecraft can't detect quakes, but the existence of young fault scarps and reactivated ancient faults strongly suggests that Mercury quakes must occur, probably frequently. Future missions to Mercury will hopefully deploy seismometers to detect and study these quakes. The pattern of seismic waves, how they travel through the planet, and how they're reflected and refracted by internal boundaries, can tell us an enormous amount about Mercury's internal structure. Seismology could precisely measure the thickness of the crust, confirm the size of the solid inner core, determine whether the stable layer at the top of the outer core really exists, and map variations in the mantle's structure and composition. All of this information is locked inside Mercury, waiting for seismometers to unlock it. The discovery of ongoing tectonic activity on Mercury also has implications for understanding the planet's thermal evolution. The fact that Mercury is still contracting measurably today means it's still losing heat at a rate sufficient to produce observable surface deformation. This constrains how much heat remains in the interior and how quickly it's escaping. Those constraints, in turn, help us understand the composition and structure of the core, the thickness and thermal properties of the mantle, and the planet's overall thermal budget. One final piece of the contraction puzzle involves the curious distribution pattern of the large lobate scarps. When scientists mapped the locations and orientations of all the major scarps visible across Mercury's surface, they discovered something unexpected and still not fully explained. The scarps aren't randomly distributed as you might expect for a process driven by uniform global contraction. Instead, they cluster in two broad bands running north-south through opposite hemispheres, roughly 180 degrees apart in longitude. Why would global contraction produce this asymmetric pattern? If the whole planet is shrinking uniformly in all directions, you'd expect scarps to be evenly distributed across the surface with no preferred locations or orientations. But that's not what we see. The concentration of scarps in these two bands suggests that something about Mercury's interior structure or the stress distribution during contraction is not uniform. Several hypotheses have been proposed to explain this pattern, though none is universally accepted yet. One possibility involves Mercury's non-spherical shape. The planet is slightly oblate, flattened at the poles and bulging at the equator because of its rotation. As Mercury contracts, this shape might focus stresses along certain latitudes, creating preferential zones for scarp formation. The geometry of how a non-spherical object shrinks could naturally produce banded patterns of deformation. Another possibility relates to ancient tidal effects from when Mercury's rotation was faster and not yet locked in the current 3:2 resonance with its orbit. Early in Mercury's history, tidal forces from the Sun would have raised bulges on the planet, and as Mercury's rotation gradually slowed through tidal dissipation, the location of these bulges would have migrated. The stress patterns associated with tidal deformation might have influenced where faults formed during the early phase of rapid contraction, setting up the banded pattern we see today. Alternatively, the pattern might relate to the structure and composition of Mercury's interior. If the mantle has lateral variations in thickness or composition, perhaps related to the giant impact that might have stripped away much of the original mantle, these variations could affect how stress is transmitted through the crust. Thicker mantle in some regions might support more stress before breaking, while thinner mantle allows faults to form more easily. This could focus deformation in bands aligned with the underlying structural variations. Whatever the cause, the banded distribution of scarps adds another layer of complexity to Mercury's tectonic story. It's not a simple tale of uniform shrinkage. Regional variations in stress, composition, thermal history, or some combination of these factors have left their mark on the surface, creating patterns we're still working to understand fully. As we await the arrival of Bepi Colombo in November 2026, the anticipation in the planetary science community is palpable. This mission represents our next great opportunity to unravel Mercury's mysteries, to build on Messenger's foundation and push our understanding to new levels of detail and sophistication. Bepi Colombo is not one spacecraft, but three traveling together as a single stacked assembly. The Mercury Transfer Module, built by the European Space Agency, provides the solar electric propulsion system that's been pushing the stack toward Mercury through a complex series of gravity assist maneuvers over the past 6 years. This module uses ion thrusters, engines that accelerate charged particles to extremely high velocities to produce thrust. Ion thrusters are very fuel efficient but produce only gentle acceleration, so the journey to Mercury requires careful planning and multiple flybys to gradually adjust the trajectory. The Mercury Planetary Orbiter, also built by ESA, carries 11 scientific instruments designed to study Mercury's surface, interior structure, composition, and tenuous exosphere. This orbiter will settle into a polar orbit, bringing it as close as 480 kilometers from the surface at periapsis, its closest approach, while swinging out to 1,500 kilometers at apoapsis. This elliptical orbit is optimized for high-resolution imaging during close approaches, while allowing the instruments to sample different altitudes and regions. The Mercury Magnetospheric Orbiter, built by the Japan Aerospace Exploration Agency and nicknamed MEO, specializes in studying Mercury's magnetic field and its interaction with the solar wind. MEO will enter a highly elliptical polar orbit, ranging from 590 kilometers at periapsis to 11,700 kilometers at apoapsis. This orbit allows MEO to sample different regions of Mercury's magnetosphere, from close to the surface, where the internally generated field dominates, to high altitudes, where the interaction with the solar wind becomes important. When the stack reaches Mercury in November 2026, the three components will separate in a carefully choreographed sequence. The transfer module, its job done, will be jettisoned and will likely crash into Mercury's surface, creating a new crater to mark the mission's arrival. The two orbiters will use their onboard propulsion systems to maneuver into their respective orbits over a period of several months. By early 2027, both spacecraft should be in their final science orbits and ready to begin the primary mission phase. Between them, these two spacecraft carry instruments of extraordinary sophistication, representing significant advances over what Messenger carried 15 years earlier. Bepi Colombo's cameras can image the surface at resolutions down to 5 meters per pixel under optimal conditions, compared to Messenger's best resolution of tens of meters. This improvement will reveal countless features too small for Messenger to detect. Hollows only a few meters across, small fault scarps, fine details of volcanic features, fresh impacts that occurred between the two missions, all will become visible for the first time. Spectrometers covering wavelengths from ultraviolet through visible and infrared to thermal wavelengths will analyze the composition of surface materials in unprecedented detail. The MERTIS instrument, a combined imaging spectrometer and thermal radiometer, will map Mercury's mineralogy while simultaneously measuring surface temperatures. 1. By observing how the surface temperature changes over the course of Mercury's long day and night, MERTIS can determine the thermal properties of different rock types, information that tells us about their composition and structure. A laser altimeter similar to Messenger's, but with improved accuracy, will map the topography with precision sufficient to detect subtle features only meters high. By comparing topographic measurements from Bepi Colombo with those from Messenger, scientists might be able to detect changes that occurred during the intervening years. Has the surface subsided anywhere? Have any scarps grown higher? Have any hollows expanded? These are the kinds of questions that comparing two high-precision topographic datasets can potentially answer. Magnetometers on both spacecraft will measure the magnetic field strength and direction at multiple points simultaneously, allowing scientists to reconstruct the three-dimensional structure of the field and the electrical currents flowing in the magnetosphere with unprecedented detail. Having two spacecraft makes an enormous difference for magnetospheric studies. With MESSENGER, we could only measure the field at one location at a time. With Bepi-Colombo's two orbiters, we can measure it at two locations simultaneously, seeing how the field varies in space and responding to changing solar wind conditions. Particle detectors will analyze the composition and energy distribution of ions and electrons in Mercury's exosphere and magnetosphere. These instruments can identify what elements are present in the exosphere and determine where they came from. Are they blasted off the surface by micrometeorites, liberated by solar wind sputtering, released through thermal processes? The energy and directional distributions of the particles provide clues about their sources and the processes that freed them. Gamma-ray and neutron spectrometers will measure the abundance of elements in the surface rocks with better sensitivity than MESSENGER achieved. These instruments detect radiation produced when cosmic rays strike the surface, and the spectrum of that radiation reveals which elements are present and in what quantities. Bepi-Colombo will produce detailed maps showing how surface composition varies across Mercury, identifying concentrations of specific elements and rock types. A sophisticated gravimeter will detect tiny variations in Mercury's gravitational field as the spacecraft orbits. Regions with more mass produce slightly stronger gravity. Regions with less mass produce slightly weaker gravity. By mapping these variations, scientists can infer density variations in the planet's interior. Is the mantle thicker in some regions? Does the crust have variations in thickness or composition? Are there buried impact basins or ancient magma chambers? Gravitational mapping can reveal all of these features. Bepi-Colombo has already made 6 flybys of Mercury as part of its complex trajectory, using the planet's gravity to help slow down and refine its approach. During these flybys, some of the instruments were activated to collect preliminary data and test their systems in the Mercury environment. The images and measurements returned from these flybys have been spectacular, providing tantalizing previews of what the main mission will deliver. During the most recent flyby in January 2025, Bepi-Colombo's monitoring cameras captured stunning images of Mercury's North Pole, peering down into permanently shadowed craters like Prokofiev, Kandinsky, Tolkien, and Gordimer, some of which harbor water ice. The images show details of the crater floors and walls never seen before, revealing the complex topography of these shadowed regions. The spacecraft also became the first mission to observe Mercury in mid-infrared wavelengths using the MERTIS instrument, providing information about surface temperatures and thermal properties even during the brief flyby. But the flybys are just appetizers. The real feast of data begins when Bepi-Colombo enters orbit and can make continuous, systematic observations over an extended period. One of the mission's key objectives is to determine the size of Mercury's solid inner core with much greater precision than MESSENGER achieved. MESSENGER provided strong evidence that the inner core exists, but couldn't measure its exact radius. The uncertainty in the measurement was too large. Bepi-Colombo's gravity and rotation experiments, combining precise measurements of Mercury's gravitational field with tracking of the planet's libration, should be able to pin down the inner core size to within tens of kilometers. This measurement matters because the size of the inner core tells us about the core's composition and thermal state. A larger inner core means more of the core has crystallized, implying either a cooler temperature or a composition that crystallizes more readily. A smaller inner core suggests higher temperatures or a composition enriched in elements like sulfur that lower the freezing point. By combining the inner core size with measurements of the total core size from gravity and the magnetic field observations, scientists can constrain how much sulfur and other light elements the core contains. Bepi Colombo will also study the polar ice deposits in far greater detail than MESSENGER could achieve. Higher resolution cameras and spectrometers will map the distribution of ice and organic materials within individual craters, identifying which craters have surface ice, which have buried ice, and how thick the dark organic layer is in different locations. The mission might even be able to determine the age of different ice deposits by looking at how many small impact craters have formed on top of the icy surfaces. Freshly deposited ice would have few craters. Ancient ice would be more heavily cratered. This could tell us whether Mercury's ice is all ancient, billions of years old, and accumulated gradually over the planet's history, or whether some deposits are recent, delivered by recent large cometary impacts. Another major objective is to study Mercury's hollows comprehensively. Bepi Colombo's instruments can measure the composition of the bright material in the hollows and the surrounding dark low reflectance material with much greater precision than MESSENGER achieved. The Mercury spectrometer, in particular, can identify specific minerals based on their thermal infrared spectra. This should finally allow scientists to identify which volatile compounds are responsible for hollow formation. Are they sulfides, as many suspect? Carbon compounds? Chlorides? Some combination? The answer lies in the spectroscopic signatures. By comparing Bepi Colombo's images of hollows with MESSENGER's images from 15 years earlier, scientists might even be able to detect changes in hollow size or morphology, confirming that these features are actively forming today, rather than being ancient relics. If a hollow has grown larger, if its edges have retreated even by a few meters, that would be direct proof of ongoing volatile loss and active surface modification. The mission will also investigate Mercury's volcanic history in unprecedented detail. MESSENGER revealed extensive evidence for volcanism, including vast plains of smooth volcanic rock covering much of the northern hemisphere, explosive pyroclastic deposits around volcanic vents, and volcanic features cutting across ancient cratered terrain. But many fundamental questions remain unanswered. When did Mercury's volcanism begin? And when did it end? What was the composition of the lavas? Were they similar to basalts on Earth and the Moon? Or did Mercury's unusual composition produce different lava types? How did volcanic activity relate to the cooling and contraction of the planet? Bepi Colombo's thermal infrared spectrometer can identify different types of volcanic rocks based on their mineralogy, distinguishing between iron-rich basalts, more evolved compositions, and exotic lava types that might exist only on Mercury. Its high-resolution cameras can map volcanic features at scales that reveal individual lava flow lobes, small volcanic vents, and fine details of pyroclastic deposits. And its timing of observations throughout Mercury's day will allow it to detect any residual volcanic heat still emanating from young volcanic features, if any exist. Although scientists don't expect active volcanism on Mercury today, the possibility can't be completely ruled out without observing the entire planet systematically over an extended period. If there is any residual volcanic activity, any warm spots indicating recent lava flows or active fumaroles, Bepi Colombo will find them. More likely, the mission will confirm that Mercury's volcanic era ended billions of years ago, but it will reveal when and how that volcanic activity operated, answering questions that have puzzled planetary scientists for decades. Bepi Colombo will also continue and expand the investigation of Mercury's magnetic field that Messenger began. MEO, the magnetospheric orbiter, is specifically designed for detailed magnetospheric studies. Its highly elliptical orbit will carry it through different regions of the magnetosphere over the course of each orbit, allowing it to sample the entire three-dimensional structure of Mercury's magnetic environment. Near periapsis, MEO will pass close to the planet where the internally generated dipole field dominates. At apoapsis, high above the surface, it will sample regions where the interaction with the solar wind becomes important, where magnetic reconnection occurs and where particles are accelerated. The dual spacecraft configuration, with MEO sampling the magnetosphere and the planetary orbiter measuring the field close to the surface, will provide unprecedented insights into how the dynamo works deep in the core, how the magnetic field emerges through the crust and interacts with surface rocks, and how it couples to the solar wind to create Mercury's dynamic magnetosphere. This information is crucial for testing theories about the offset dipole field, the asymmetric field strength between hemispheres, and the possible existence of a stable layer at the top of the liquid outer core. One of the key questions Bepi Colombo will address is how Mercury's magnetic field varies over time. Does the field strength change measurably over months or years? Do the locations of maximum and minimum field strength shift? Is there any evidence for secular variation, the slow changes in Earth's magnetic field that occur as the convection patterns in the core evolve? By monitoring the field continuously over at least one Earth year, possibly two if the mission receives an extension, Bepi Colombo can track these temporal variations and use them to understand the dynamics of Mercury's dynamo. Mercury's story, as we're discovering it piece by piece through decades of observations and missions, is ultimately our story. This small, peculiar world holds clues to fundamental questions about how planets form, how they evolve over billions of years, and how they eventually cool and become dormant. Every mystery we unravel about Mercury teaches us something profound about the processes that shaped Earth, Mars, Venus, and the countless rocky exoplanets we've discovered orbiting other stars throughout our galaxy. The liquid core mystery reminds us that planetary evolution is more complex and varied than our simplistic models suggest. Small planets don't always cool quickly and become geologically dead within the first billion years. Composition matters enormously. Internal structure matters. Mercury's sulfur-rich core acts as a chemical time capsule, preserving conditions that allow a dynamo to operate billions of years longer than we'd expect for a planet of this size. This has implications for understanding magnetic fields around exoplanets. Many of the rocky exoplanets we've detected are similar in size to Mercury, or even smaller. Do they have magnetic fields? For how long can they maintain them? Mercury provides the only data point we have for planets in this size range. The hollows challenge our assumptions about what materials can survive where in a planetary system. Volatile elements we thought couldn't exist in the inner solar system, especially not at Mercury's orbital distance, where the sun's heat and radiation are so intense. Mercury's hollows prove otherwise. They demonstrate that planets can retain surprising chemical diversity despite hostile environments. This has far-reaching implications for understanding the volatile budgets of all the terrestrial planets, including Earth. Where did Earth's water come from? How much of it was delivered by comets and asteroids after the planet formed? And how much might have been present in the materials that first accreted to form Earth? These are not just academic questions. They're central to understanding how Earth became habitable, how it developed the oceans and atmosphere that made life possible. Mercury's water ice deposits and volatile rich hollows provide a natural laboratory for studying these questions. The polar ice represents billions of years of cometry and asteroidal impacts frozen in time. By analyzing its composition, its isotopic ratios, and the organic materials mixed with it, we can reconstruct the history of volatile delivery throughout the inner solar system. This tells us about the conditions present when Earth was forming and when life first arose in Earth's oceans billions of years ago. The ongoing contraction of Mercury demonstrates that even small planets can remain tectonically active for billions of years, challenging the conventional wisdom that planetary activity is limited to large bodies like Earth. This expands our understanding of what kinds of worlds might be geologically active and for how long. As we discover more rocky exoplanets, many of them smaller than Earth, Mercury teaches us not to dismiss them as dead worlds. They might harbor ongoing geological processes that could affect their habitability, their atmospheric evolution, or their potential to develop and sustain life. Mercury also serves as a natural laboratory for studying extreme environments and the physical processes that operate under such conditions. The planet experiences temperature variations that would destroy most materials we're familiar with on Earth. Intense solar radiation that breaks chemical bonds and drives photochemistry. A weak but dynamic magnetic field that undergoes complete reconfiguration cycles every 2 minutes. Negligible atmosphere that exposes the surface directly to space. These conditions test our understanding of physics, chemistry, and geology in ways that studying Earth alone never could. The magnetosphere, in particular, is a unique system found nowhere else in the solar system. Nowhere else can we observe such rapid dynamics, with the entire magnetospheric configuration cycling through loading and unloading phases every 2 minutes. This makes Mercury an ideal natural laboratory for studying fundamental processes like magnetic reconnection, particle acceleration, and plasma physics under extreme conditions. Understanding these processes at Mercury helps us interpret observations of stellar flares on other stars, accretion disks around black holes, and other high-energy astrophysical phenomena where similar physics operates but where we can't make detailed in-situ measurements. Looking forward to the more distant future, Mercury might someday play a role in human space exploration, though that possibility remains speculative and decades away at minimum. The polar ice deposits, if they prove accessible and economically viable to extract, could provide water and fuel for spacecraft operating in the inner solar system. Water is incredibly valuable in space, not just for drinking but for radiation shielding, oxygen extraction, and conversion to rocket propellant through electrolysis. Solar power is extraordinarily abundant at Mercury. The sunlight is 7 times more intense than at Earth's orbit, making solar panels 7 times more efficient per unit area. This abundance of energy could power industrial processes, life support systems, or spacecraft recharging stations. The planet's position deep in the sun's gravitational well makes it an ideal location for studying our star with space-based instruments, observing solar activity, and monitoring space weather that affects all the inner planets. Mercury's orbital position could also make it valuable for gravity assist maneuvers. spacecraft heading to the inner solar system, or using the Sun's gravity for missions to the outer planets might use Mercury for course corrections and velocity changes, similar to how missions use Venus and Earth today. Establishing infrastructure at Mercury, even something as simple as navigation beacons or communication relays, could facilitate future deep space exploration. But these are distant possibilities, entertaining to contemplate, but not the focus of current scientific investigation. For now, our emphasis is on understanding Mercury for its own sake, on solving the mysteries that have tantalized us since Mariner 10 first revealed this strange little world nearly 50 years ago, on building a comprehensive picture of how this planet works and why it behaves so differently from what our theories predict. We've come remarkably far in our understanding over the past few decades. Messenger's 4-year orbital mission transformed Mercury from the least explored to one of the best studied terrestrial planets. We've mapped its entire surface, measured its composition, confirmed its liquid core, discovered its ice deposits, identified its hollows, tracked its ongoing contraction. Each discovery opened new questions even as it answered old ones. Yet so many fundamental questions remain. How exactly does Mercury's dynamo operate? What physical mechanism creates the offset dipole configuration? Why is the field so much stronger in the northern hemisphere? What processes regulate the stability and thickness of the layer at the top of the core, if indeed such a layer exists? These questions about the magnetic field and core dynamics remain partially answered, understood in broad outline but not in detail. Which volatile compounds form the hollows? Are they sublimating actively right now at measurable rates? How rapidly are the hollows growing? What does their distribution tell us about Mercury's crustal composition and the vertical structure of volatile bearing materials? The hollow mystery remains one of Mercury's most intriguing puzzles, a phenomenon unique to this planet that we're still working to fully explain. How much water, ice exists at the poles in total? How thick are the deposits in the deepest craters? How old is the ice? Are all the deposits ancient, or do some represent recent deliveries? What are the organic materials mixed with the ice? And what do they tell us about the composition of comets and asteroids that struck Mercury over billions of years? Could these organic materials have relevance for astrobiology, for understanding the chemical building blocks that were available in the early solar system when life emerged on Earth? The ice deposits hold answers to these questions, but we need more detailed observations and eventually sample return to unlock them fully. Are Mercury's fault scarps still slipping today? How frequently do Mercury quakes occur? What magnitudes do they reach? What do the seismic waves tell us about the planet's interior structure, the thickness of the crust, the properties of the mantle? When exactly did Mercury's volcanism end? Is there any possibility, however remote, of residual volcanic activity today, perhaps in the form of outgassing or minor heat flow from the interior? What drove the explosive eruptions that created Mercury's spectacular pyroclastic deposits? And what does this tell us about the volatile content of Mercury's mantle? These are not idle questions posed out of mere curiosity. Each one connects to deeper questions about planetary science, about how worlds form and evolve, about the diversity of geological processes in our solar system and beyond. Bepi Colombo will help answer many of these questions when it begins its orbital mission in early 2027. Future missions, perhaps including landers that can place seismometers on the surface, rovers that can study rocks in detail, or Even sample return missions that bring pieces of Mercury back to Earth for laboratory analysis will address others, and some questions might remain unanswered for decades or even longer, waiting for new technologies, new mission concepts, or new ways of thinking about the data we already have. Science progresses through this iterative process of observation, hypothesis, testing, and refinement. Each mission builds on previous discoveries. Each generation of scientists re-examines old data with fresh perspectives and new analytical tools. What seemed impossible to understand in one era becomes clear in the next. What we can say with complete certainty is that Mercury is not the simple dead world we once thought it was. It's a planet of profound contradictions that make it endlessly fascinating to study. The hottest daytime surface temperatures in the solar system, yet ice persists in permanent shadow at the poles. The smallest terrestrial planet, yet the densest. An enormous iron core that should have solidified billions of years ago, yet remains partially molten. A surface that should be depleted of volatiles, yet harbors hollows formed by sublimating compounds and pyroclastic deposits created by explosive volcanic degassing. Ancient terrain billions of years old, marked by craters from the early solar system bombardment, yet tectonic features forming today as the planet continues to contract. These contradictions make Mercury a perfect subject for scientific inquiry. It's accessible enough that we can study it with current technology, sending spacecraft to orbit it and observe it in detail. Yet it's strange enough that it constantly surprises us, defying our expectations and forcing us to think more carefully about our assumptions. Close enough that we can reach it with robotic missions within a few years of flight time, yet different enough from Earth that it challenges our Earth-centric thinking about how planets should behave. Small enough to seem simple at first glance, just a ball of rock and metal without the complex atmosphere, oceans, and life that make Earth so intricate, yet complex enough internally and geologically that it has kept scientists puzzling over its mysteries for the 50 years since Mariner 10's first flyby. Every time we think we understand Mercury, it reveals something new that doesn't quite fit our models, something that requires us to look closer, think harder, and expand our theories. As Bepi Colombo makes its final approach to Mercury over the coming months in 2026, as it slips into orbit in November and begins its systematic study of the planet that will continue for at least a year and hopefully longer, if mission extensions are funded, we stand on the threshold of a new era of Mercury science. The discoveries of the next few years will reshape our understanding, not just of this one small world, but of planetary processes throughout the solar system and beyond. The data Bepi Colombo returns will keep scientists busy for years, probably decades, analyzing all the images, processing the spectroscopic data, modeling the magnetic field observations, interpreting the gravity measurements, comparing results from different instruments, building comprehensive models that explain all the observations coherently. This work will continue long after the spacecraft itself falls silent, long after it exhausts its fuel and either crashes into Mercury's surface or is left in a stable orbit as a monument to human curiosity and ingenuity. Mercury, the planet that breaks all the rules, the shrinking world with ice at its poles and a heart that refuses to grow cold, continues to reveal its secrets. And we, curious, persistent, determined to understand this strange neighbor that shares our solar system, continue to listen, to observe, to measure, to think. The smallest planet in our solar system has proven to be one of the mightiest teachers, showing us that size isn't what matters in planetary science. Activity knows no size limits, Complexity hides in unexpected places, and the most profound lessons often come from the worlds we least expected to teach us anything at all. This is Mercury, closer than most people realize, orbiting the Sun every 88 days in an elliptical path that brings it from 47 to 70 million kilometers from our star. Stranger than anyone imagined before we sent spacecraft to study it up close, and still full of surprises that await discovery by Bepi Colombo and future missions. From its liquid iron core still churning billions of years after formation, defying every prediction about how quickly small planets should cool and solidify, to the hollows etching themselves into its surface at this very moment, removing volatile materials that shouldn't even be there according to our formation models, to the ancient fault scarps that still slip and quake, accommodating ongoing contraction as the planet shrinks measurably in our own geological epoch. Mercury shows us that geology knows no size limits, that activity persists far longer than simple models predict, and that complexity and mystery exist everywhere we look in our solar system, if we just take the time to look carefully enough. The smallest world among the 8 planets orbiting, our Sun turns out to be anything but small in the questions it raises and the insights it provides into how planets work, how they form, and how they change over billions of years of cosmic time. The implications of Mercury's ongoing activity extend far beyond this single planet. Every discovery we make about Mercury informs our understanding of planetary evolution as a universal process. When we detect small planets orbiting other stars, planets similar in size to Mercury, we can now make more informed predictions about their internal structures, their magnetic fields, their geological activity, and their long-term evolution. Before Messenger, our models suggested that Mercury-sized planets should be geologically dead, their cores frozen solid within 1 billion years of formation. Now we know better. Now we know that composition matters as much as size, that the presence of light elements like sulfur can dramatically extend the lifetime of a planetary dynamo. This knowledge changes how we think about the habitability of small, rocky exoplanets. A magnetic field protects a planet's atmosphere from being stripped away by stellar winds. Without magnetic protection, a planet can lose its atmosphere over millions or billions of years, rendering it uninhabitable even if it started with favorable conditions. Mercury's persistent magnetic field, maintained by its sulfur-rich core, tells us that even small planets can retain magnetic protection for billions of years under the right circumstances. This matters when we evaluate the habitability potential of the countless small rocky planets discovered by the Kepler Space Telescope, the TESS mission, and ground-based planet hunting programs. The tectonic activity we're observing on Mercury also has implications for understanding planet-wide stress patterns and how they evolve over time. Earth's plate tectonics is driven by a combination of cooling from above as cold oceanic lithosphere sinks at subduction zones and heating from below as hot mantle material rises beneath mid-ocean ridges. This two-way convection system is probably unique to Earth among the terrestrial planets. Venus appears to have a very different tectonic style, possibly involving episodic global resurfacing events rather than continuous plate motions. Mars had early tectonic activity, but appears to have shut down billions of years ago as its interior cooled. Mercury represents yet another tectonic style, what we might call contractional tectonics, driven purely by thermal evolution. As the planet cools and shrinks, the lithosphere accommodates the change through thrust faulting and folding. This style of tectonics might be common among small rocky bodies throughout the solar system and beyond. Moons like Enceladus and Europa show evidence of tectonic activity driven by tidal heating rather than internal radioactive decay. Mercury shows us what tectonics looks like when driven solely by secular cooling, by the slow radiation of primordial heat into space. Understanding these different tectonic styles helps us build a more complete theory of how planetary surfaces evolve. Not all planets have plate tectonics like Earth. In fact, Earth might be the exception rather than the rule. By studying Mercury, Venus, and Mars, we learn about the range of tectonic processes that can operate on rocky planets. This knowledge will be essential when we eventually get high-resolution images of rocky exoplanet surfaces and try to interpret the geological features we see. The hollows on Mercury's surface represent another phenomenon that might exist elsewhere but has never been recognized because we've never looked in the right place or at the right scale. Are there hollows on Venus, hidden beneath the thick clouds that prevent us from seeing surface details smaller than a few hundred meters? Could hollows exist on Mars in regions where volatile rich minerals are exposed by impacts or erosion? Do any of Jupiter's or Saturn's moons have hollows forming through sublimation of exotic ices exposed on their surfaces? We won't know until we look carefully, using the knowledge gained from Mercury to guide our searches. Mercury taught us what hollows look like, how they form, and where to expect them. Now we can apply that knowledge to interpret observations of other worlds. Perhaps Messenger's discovery of hollows on Mercury will lead to the recognition of similar features elsewhere. Features that were always there but that nobody noticed because we didn't know to look for them. The water ice at Mercury's poles also has profound implications beyond the planet itself. The fact that ice can survive and accumulate even in such an extreme environment tells us that permanently shadowed regions are effective cold traps anywhere in the solar system. This principle, proven at Mercury, applies equally well to the Moon, to Mars, to asteroids, even to large Kuiper Belt objects. Wherever you have surfaces with low enough temperatures and permanent shadow, you can trap and preserve volatile ices over geological timescales. This is why NASA's Artemis program is so interested in the Moon's south pole, where permanently shadowed craters similar to Mercury's polar craters harbor water ice. This is why future Mars missions will target the polar regions to search for accessible ice deposits. This is why asteroid mining concepts often focus on volatile-rich asteroids that might contain water ice in their interiors. Mercury showed us the way, demonstrated that cold traps work even in seemingly impossible locations, and proved that water ice is more widespread in the inner solar system than anyone imagined. The organic materials found mixed with Mercury's ice also have astrobiological significance. These carbon-rich compounds, delivered by comets and asteroids over billions of years, are the same types of materials that were delivered to the early Earth. When Earth formed 4.5 billion years ago, it was probably dry and depleted in volatile elements, just as Mercury is today. But impacts from water-rich comets and carbonaceous asteroids delivered the water that filled Earth's oceans and the organic compounds that became the building blocks of life. By studying the composition of Mercury's ice and the organic materials in the dark layer covering it, we're studying the raw materials that were available in the early solar system. We're analyzing the stuff that rained down on all the terrestrial planets during the late heavy bombardment. That period, about 4 billion years ago, when the inner solar system was still being pelted by countless impacts. Some of those impacts delivered the ingredients for life to Earth. The same types of materials that are frozen at Mercury's poles were delivered to Earth in vastly larger quantities and some of those molecules ended up incorporated into the first living cells. Understanding what organic molecules exist at Mercury, what their structures and isotopic compositions are, helps us understand the prebiotic chemical inventory that was available on the early Earth. This informs our theories about how life originated, what chemical pathways might have led from simple organic compounds to self-replicating molecules to the first primitive cells. It also informs the search for life beyond Earth. If we know what organic materials were delivered throughout the inner solar system, we can make better predictions about what might exist on Mars, on Europa, on Enceladus, on Titan, on the countless exoplanets in other star systems. Mercury also offers valuable lessons about planetary magnetospheres and how they protect planets from stellar radiation and particle bombardment. Mercury's magnetosphere is weak, allowing significant amounts of solar wind to reach the surface and drive space weathering processes. This makes Mercury a useful case study for understanding what happens to planets that have weak magnetic protection, or none at all. Mars lost its magnetic field billions of years ago and subsequently lost most of its atmosphere to solar wind stripping. Venus never had a magnetic field, or lost it very early, and its atmosphere has been sculpted by direct interaction with the solar wind over billions of years. Mercury still has a magnetic field, but it's so weak that the planet provides a middle ground, a case where magnetic protection exists but is limited. By studying how Mercury's surface and exosphere respond to solar wind bombardment despite the magnetic field, we learn about the effectiveness of weak magnetic fields at planetary protection. This knowledge applies directly to evaluating the habitability of exoplanets. Many of the rocky exoplanets we've discovered orbit M-dwarf stars, red dwarfs that are smaller and cooler than our Sun, but much more active, producing frequent flares and powerful stellar winds. A planet in the habitable zone of an M-dwarf faces a harsh radiation environment. Does it need a magnetic field to remain habitable? How strong must that field be? Can a weak field like Mercury's provide meaningful protection? Or does a planet need a strong field like Earth's? Mercury provides data points for answering these questions. We can measure how much atmosphere or exosphere Mercury loses to the solar wind despite its magnetic field. We can quantify how the magnetosphere deflects and channels solar wind particles. We can determine what fraction of the surface is shielded versus exposed to direct bombardment. All of this information helps us model planetary habitability around active stars. The comprehensive picture of Mercury that's emerging from MESSENGER's data and will be refined by Bepi Colombo tells a story of a planet that never stops surprising us. At every stage of exploration, from ground-based telescopic observations to Mariner 10's flybys to MESSENGER's orbital mission, Mercury revealed unexpected features and behaviors. The pattern continues with Bepi Colombo. Even before entering orbit, the mission's flybys have revealed new details about hollows, fresh observations of the magnetic field, and the first mid-infrared observations of the surface. What will Bepi Colombo discover when it settles into orbit and begins systematic observations? What features will emerge when we image the surface at 5-meter resolution instead of tens of meters? What new details about the magnetic field structure will two simultaneous spacecraft reveal? What will we learn about the ice deposits from higher resolution mapping and spectroscopy? These questions will be answered over the next several years as Bepi Colombo carries out its mission. But beyond the specific scientific questions, there's a deeper lesson that Mercury teaches us about doing science itself. Assumptions are dangerous. Simple models often fail when confronted with complex reality. The universe is under no obligation to behave the way our theories predict. Mercury shouldn't have a liquid core, but it does. It shouldn't contain significant amounts of volatile elements, but it does. It shouldn't be tectonically active after billions of years, but it is. Every one of these discoveries required us to revise our thinking, to develop more sophisticated models, to recognize that reality is richer and more nuanced than our simple theories suggested. This humility in the face of nature's complexity is essential for scientific progress. Every time a new mission returns data that doesn't quite match predictions, there's a temptation to dismiss it as error, to assume the instruments malfunctioned or the analysis was wrong. But more often than not, when careful analysis confirms that the data is real, it's our theories that need revision. Mercury has taught this lesson repeatedly. The planet is a reminder that we should expect surprises, welcome them, embrace the opportunity they provide to deepen our understanding. As we look toward the future of Mercury exploration, several possibilities emerge for missions beyond Bepicolombo. A lander mission could place seismometers on the surface to detect Mercury quakes and map the interior structure with seismic waves. It could analyze rocks chemically with instruments more sophisticated than what can fly on orbiters. It could directly observe space weathering processes by monitoring how surface materials change over time. A lander could also study the polar ice deposits in detail, perhaps drilling into them to extract cores that reveal the depositional history layer by layer. A sample return mission, though enormously challenging given the energy requirements to reach Mercury and return, would allow laboratory analysis of Mercury rocks with instruments far more sensitive than anything we can send to the planet. We could determine precise ages of rocks through radiometric dating, measure isotopic ratios that reveal information about Mercury's formation and thermal history, identify minerals and their chemical compositions with electron microscopes and mass spectrometers, analyze volatile content and distribution with unprecedented sensitivity. These future missions remain concepts for now, ideas being studied and refined but not yet approved or funded. They depend on technological developments, budget priorities, and the continued interest of the scientific community. But the path forward is clear. Mercury has proven itself worth studying in detail. Each mission has raised new questions, even as it answered old ones. The planet will keep revealing secrets for as long as we keep looking. In the just grand scheme of our solar system, Mercury might seem insignificant. It's tiny, barely larger than our moon. It has no rings like Saturn, no giant storm systems like Jupiter, no vast canyons like Mars, no liquid methane lakes like Titan. It orbits so close to the Sun that observing it from Earth requires skill and patience, catching it in twilight before it disappears into the Sun's glare. For most of human history, it was just a wandering star, a bright point of light that moved mysteriously across the sky. But now we know better. Now we understand that this small, battered world harbors mysteries as profound as those of any planet in our solar system. A core that shouldn't be liquid, but is. Ice that shouldn't survive, but does. Tectonics that should have stopped billions of years ago, but continues. Hollows that reveal the planet is still actively losing material to space. A magnetic field generated by processes we're still working to fully understand. Mercury reminds us that wonder and mystery exist everywhere if we just look closely enough. That the smallest members of our solar system family have stories as compelling as those of the giants. That assumptions based on simple models often fail when confronted with nature's complexity. That every world is unique, shaped by a particular combination of formation history, composition, orbital dynamics, and evolutionary processes that produces something unlike anything else. This is the lesson of planetary science in general, and Mercury in particular. Each world tells its own story. Each has experienced a unique sequence of events over billions of years that has made it what it is today. Earth's story involves plate, tectonics, and the emergence of life. Mars tells a story of lost oceans and a fading magnetic field. Venus speaks of a runaway greenhouse and global resurfacing. And Mercury tells a story of resilience and persistence, of a small planet that refuses to go quietly into geological dormancy, that maintains a liquid core and active surface processes long after conventional wisdom says it should have frozen solid. As Bepi Colombo approaches its destination, as scientists around the world prepare for the flood of data that will arrive when the mission begins its systematic observations, the anticipation builds. What new mysteries will be revealed? What old puzzles will be solved? What unexpected features will emerge when we examine Mercury at resolutions and sensitivities never before achieved? The answers await us in November 2026, when Bepi Colombo arrives and begins to unlock Mercury's secrets with the most sophisticated suite of instruments ever sent to the innermost planet. Until then, Mercury continues its endless dance around the Sun, shrinking slowly, releasing volatiles into space through its hollows, preserving ice in its polar shadows, generating magnetic fields in its churning core. The smallest planet with the biggest mysteries, the closest world to our star with ice in eternal darkness, the ancient cratered surface marked by features forming today. This is Mercury, still surprising us, still teaching us, still reminding us that the universe is stranger and more wonderful than our theories can capture, and still waiting to reveal its deepest secrets to those patient and curious enough to listen. The journey of understanding Mercury has taken us from ancient astronomers tracking a wandering star, to Galileo's telescopic observations, to Einstein using the planet's peculiar orbit to validate general relativity, to Mariner 10's first close-up images, to Messenger's comprehensive orbital survey, and now to Bepi Colombo's upcoming arrival. Each step in this journey has revealed the planet in greater detail, has answered some questions while raising others, has replaced simple pictures with complex reality, and the journey continues. Future missions will delve deeper into Mercury's mysteries. Future scientists will build on the foundation we're establishing now. Future discoveries await that we can't even imagine yet, surprises that will challenge our understanding and force us to think in new ways about how planets work. Mercury teaches us patience. It took 33 years between Mariner 10's last flyby and Messenger's arrival at Mercury. It will be 11 years between Messenger's crash into the surface and Bepi Colombo's orbital insertion. Scientific progress happens slowly, mission by mission, discovery by discovery. But it happens. Our understanding deepens. The picture becomes clearer. And with each new piece of data, we move closer to truly understanding this remarkable world. So as we close this exploration of Mercury's mysteries, we don't conclude with final answers. We can't, because the questions are still being refined and the answers are still emerging. Instead, we acknowledge the progress made, celebrate the discoveries achieved, and look forward with anticipation to what comes next. Mercury has been generous with its secrets so far. There's every reason to believe it has more waiting to be discovered by those willing to journey to the edge of the Sun's domain and look closely at the smallest planet that could.